superconducting magnetic energy storage system, supercapacitor part, batteries part, and also flywheel energy storage system. These things that we said, and also the importance of the energy storage elements for your distributed energy sources, how it is going to play an crucial role in the development of distributed energy sources that we are discussing in our previous class. And one more thing, that the existence of distributed energy sources is hard to imagine without the storage system. This is what that we have seen in our previous class. Each and every distributed energy resource is associated with a kind of a storage system. And also in storage system that we discussed about the what kind of either it can be of a transient conditions or of steady state operation, which type of storage device should enter into the domain to provide the required load power. Okay. Always that we said that one more thing, load is the master and the follower is the source. Okay. This is all. What type of sources that we have come across in my block diagram? Can any one of you imagine what are the different sources are there in my system from the previous session? What are the different sources that we have seen? Yes, battery is one source. Yeah, supercapacitor. Okay. Yeah. Yeah. Okay. Yes. Any one of you can get. Yeah. Battery, supercapacitor, sure. But the flywheel, it is a storage. We have given the overview about this kind of storage system, but the flywheel is not incorporated. And major block diagram. One more source. It is a what type of converter that we are about to discuss? What type of, means like it is a converter that we are going to have the discussion. DC, bidirectional DC-DC converter that we are going to have. But the type of source, we are saying that what are the, it is a multi-input source system. Multi-input source system. Multi-input source, there are the two things what we said. One is the battery we said, supercapacitor is said. And another one is of a solar photovoltaic system. This is what we are going to see that. And also in terms of the control aspect also that we have come across control aspects. Individual means like we have the active control system, passive, passive, hybrid and the active control system. Three types of control that we have come across. Yeah, I will show you. Yes, these are the active, parallel, passive system, cascaded system and the active parallel system that we have come across. That we said among these types of controllers, one is the more popular, what we can say that it is the active system, active parallel block system, that we can say that. So here, then what parameters are we going to control? What parameters that we are, each and every system is associated with a storage element. Okay, that the storage element has to respond according to the requirements of the, means as per the requirements of your load system. Okay, load, that the load requirement either it can be of starting conditions or of running conditions or of decelerating condition, that you may define the, means load profile. According to the load profile that the system is supposed to react. Okay, whether starting condition you require the more power and during running condition you require the less power to maintain the voltage, and then during the deceleration that we have to feed back to the system. These are the three profiles, means like we are going to see that. So then to get control over this profile, what control loop that you are supposed to have? One we said, stressed this point also, that any system that you have the two controllers are there. One is the outer loop control and the second one is of inner loop control. That we said and also posed the discussion on it. Outer loop is of voltage control loop and the inner loop is of a current control loop, and three layer structure that we have come across. One is the middle layer, outer layer and the inner layer, and also that the power splitting concepts. What is the power splitting concepts also that we are trying to convey those things. Yes? Yeah. Yes? Have you recollected all the things? Yeah. Means like we have the what we are going to see, why we are going to have the this kind of individual control will be there, that we have the full control over the individual storage element, whereas we have here in this case that we have the control, but we have the cascaded part. We will be dependent on the other type of control here. But here we have the independent control, that we have the individual converter, we have the independent control, full control over the system. Here that the control is what we are going to do, the play with the voltage and the current element. This is what we are going to see. And also we said that the power flow is going to be bidirectional power flow. One power flow, that what we are saying, that input to the means the source to the load and load to the source. This concept is of popular. And the another thing is that after having the means that is common way that we can say that the power flow diagram, what here, yeah, I can, yeah, sorry. Power flow, what we are saying that here, yeah. Now we will discuss this one block diagram. Here what we are saying that the power flow, we said this is the from source to the load, okay, and then what we can say that load to the source, but we have made use only two types of sources here, okay. In this one we need the bidirectional DC-DC converter. This is what we said. Now we will make a move to the next part of the topic, that the energy storage technologies for renewable energy sources, that is the part 2. In this part 2, that will have more focus on the DC-DC converters and its implementation, how we are going to how we are energy storage elements for renewable energy sources, so part 2. Here what we are going to do now, so far we have the fundamentals regarding the energy storage element. Now how we are going to apply this energy storage system for our renewable energy sources by using the bidirectional DC-DC converter, okay. The major part, they will say that you got the sufficient, this is what storage is very important, and the power electronics engineers are going to play a crucial role in the development of the bidirectional means like converters for the storage elements. That the storage will be there. Initially we have the talk between the power transfer from the source to the load and load to the source. Then also during some other situations, if you see the block diagram, here this case what we are having, what are the different sources that we are having for this system. I mean to say that we have the PV panel one source, and then it is connected to a DC microgrid, and another system through bidirectional DC-DC converter, a battery and supercapacitor is connected to the DC system, and the different DC load that can be of anything like a lighting load or of a fan load, or it can be of a motor load also, that you can say that we want to stabilize this DC microgrid, okay. Either it can be of a standard voltage what you are taking into the consideration, either 24 volts or of a 48 volts DC bus that you are going to take into the consideration, okay. And one more thing, this is a conventional way of representing the block diagram. I included to the best of thing all the components in it, But when it comes to this one, battery, supercapacitor, and in we are going making an assumption that this is battery. Battery means not a single cell, that we are considering it as a battery pack. A bulk of battery cells are connected in series or cascaded connection to get the required voltage. Okay, that we can say that this is 12 volts for experimentation. 7 ampere hours that we have taken experimentation. This is supercapacitor, 58 farads supercapacitor that we have taken with a voltage rating of 15 volts, and current rating is of very high, more than 1000 ampere. And then this is yeah.
Is it possible to maintain the DC voltage by using that configuration?
That
12 volts configuration.
yeah.
Is it possible to get DC capacitor at around 400?
Yeah, that will be, means like initially our testing is meant if you want to go for the DC link capacitance of 400 volts, these are not that is the disadvantage of the supercapacitor. What we can say that the voltage rating of the supercapacitor is of very low. You require to have the cascading series connection. If you connect now the individual modules, that I think one figure I have shown here in this one. If you see this one here, what we have done, two modules which are connected in series. This connection is in series case. That the 15 volts maximum rating of individual capacitor. Then maximum that we made it 30 volts. But in reality applications also very low as compared with our what we conventional electrolytic capacitor. This series it poses the voltage balancing condition also. For that reason I stressed about this kind of cell voltage balancing techniques also. If you make use, that it will give the required rating, but size of the system is going to be very big. Okay, the intention of having this supercapacitor part also is for not for the long term purpose, it is for the short term purpose. Even for 10 to 15 means like I mean to say that either 10 seconds to 15 seconds will be there. Less than, I mean to say that it is of 1 minute time period that can be maintained. Your transient period also do exist for very short period. I am not whether 10 seconds or of 10 minutes, I will give the clarity on. So then this is the thing. Now we have bidirectional DC-DC converter. All the time that you are seeing that PV panel is associated with a boost converter to meet the DC bus voltage. Okay, either it can be of 48 volts or of 24 volts that we have taken the standard system in our place. So loads, either it can be lighting, fan, these things can be made use for our system. If you see that, okay, now the system, earlier system, what are the different sources that we are having? One PV source, and the other one is of a battery source, and the other one is of a supercapacitor source. That the same thing that we have projected here. This is the block diagram and the power splitting strategy, different controls for the different sources. DC microgrid, that the load part that we are not giving means like it is simply that we are saying that it is of a microgrid, but it can be of electric vehicles or it can be of a AC microgrid also, that we may consider. For our feasibility, that we have taken not to make more complication about the circuit, that we made use of only direct DC microgrid system. If you see that this one is of a PV panel, and then it is of a battery bank module, and this one is of a supercapacitor. Okay, and during this one we are going to measure the voltage and the current of individual converter module. Then that can be compared. You know, this is the what we can say that, and also one more assumption that we are making use that this PV panel is operating under the maximum power point tracking condition. We have that the work also, it is giving the maximum output. Okay, that our interest is to have control over the all these elements, not on the PV panel. we'll say we made an assumption that this one is working under the maximum power point tracking condition. We have taken the output voltage and the means reference voltage, that is external, and the inner one we are having the means like super capacitor voltage reference, and then this one is battery voltage, battery current, but it is supposed to be battery current, battery voltage as well. So then afterwards we have the inner control. This is the externally it is supposed to be the voltage, and then inner control that we are having what we have current control. For these are of all these things are of individual converter. This one is meant for this PV panel, and then this one is this second one, and then this one is meant for the super capacitor. This is supposed to be here, that is the super capacitor part, and then this third one is supposed to be the first one, photovoltaic side. Then this one is supposed to be the second one. Okay, that the control. Now external control and the inner means like external and the internal control, that we mean to say that. Okay, then afterwards, after making a comparison with the PWM carrier signal and the reference signal, that the PWM signals will be given to the respective converters. Okay, this is one. And this one you have the power splitting, how the power splitting is taking place depending on the condition, means like how much power that you want to have during the transient condition, which type of source should come into the line to provide the required power to your system, that can be decided by this algorithm, power splitting strategy and the energy management system that it will divide. Means I mean to say that power splitting is nothing but among these three types of storage systems, which one supposed to come into the picture to provide the required power, how much percentage, either 50-50% or 75-25% or 25-75%, like that. That can be decided by this algorithm. This is the main the agenda of incorporating this power splitting algorithm is there to protect your storage system. Means like battery span, we don't want to give more stress on your battery system. Means sudden jerk or of sudden means jerk in the sense that suddenly jumping from 0 kilometers to the 100 kilometers or from 100 kilometers to 0, instead of having sudden stress over the battery module, that slowly means like in a what we can say that in a means like slowly that we are going to reach it to the steady state condition. That during this transient period also, that can be after reaching the 50% of your transient period, then the now below the 50% of your period, that can be taken by the super capacitor, and after reaching it 75% super capacitor and the 25% should be like a battery, and after reaching to the steady state condition 100% will be taken by the battery part also. In that way that we have defined the algorithm, performed the experimentation, this thing. This is one condition, means like what we are saying that we created the disturbances at the source side as well as the disturbances at the load side also, that we have done the disturbances, then we got. So if you see that this case, yeah, fine. So if you see that what we are DC microgrid configuration with the battery and super capacitor as well as the PV panel is shown. PV generation is controlled by MPPT control. Okay, that even this PV panel also, that the emulator that we have considered the direct DC source, assuming that it is operating in the maximum MPPT condition. Is it fine? My voice is audible? Yes? Okay. Yeah, fine. Now I can say that this is the portion of work, and then whenever the PV source power is more than the load demand, that the surplus power will store at hybrid energy storage system. Okay. If there is surplus power with the PV source during daytime, it is a stochastic in nature, that you can say that if it is going to produce more power, that can be stored by using the storage elements. Okay. That is the hybrid energy storage. Which one is hybrid energy storage system? This is the concept that we are making, both the supercapacitors and the battery packs. It forms the hybrid energy storage system, where if the source is more enough, then the surplus power that can be stored in the hybrid energy storage system. So, if it is storing the energy, means it is like a charging operation. Okay. Charging operation, what type of conversion is going to take place? What type of DC-DC converter operation? Buck converter. For charging part, it is the buck conversion. For discharging, it is the boost operation, that I will show you. So, at the time of deficit power, when the PV is not in a position to supply the surplus power, that the hybrid energy storage system can take care the additional power demanded by the load network. This one will enter into the picture without interrupting to your load part, master load part. This will come and provide the constant power supply to your system, so that we will not feel, means like that the system will not experience any kind of fluctuations in it. Okay. This is one. So, now, yes, okay, now all the system is fine. This is what we are having. Now we will go by the depth about this one. How the supercapacitor is going to look like. Okay, that the mathematical modeling of the storage systems. So, here in this mathematical modeling of the supercapacitor, it is like a ordinary electrolytic capacitor, what we said, without the presence of the dielectric material. It is having that the equivalent series resistance in the case of supercapacitor is lower as compared with the conventional electrolytic capacitor. Okay. That's what we said, that we are having the, even though it is having that the equivalent model, equivalent series resistance represents the power loss in supercapacitor. C1 and is the main energy storage storing capacity of the supercapacitor. R1 accounts for the self discharge, even though this one it is having the self discharge. RP and CP, which are responsible for the fast dynamics in supercapacitor. Okay. This is what the model of a supercapacitor that we have taken into the consideration for mathematical means MATLAB simulation part. So, now how so then this one, then next when it comes to the, means like you will say that the system is of fully charged or of partially charged. How you are going to say that? When the system is of, that the initial question that I posed, that if the system is of fully charged condition, what do you mean? That the voltage that the voltage rating is equal, voltage of your storage element is equal to the rated voltage, then the system is a fully charged condition. Depending on the voltage factor, that you are going to define that whether the system is of means how much charge is left out, and some parameters that you are going to take into the consideration, that is the state of the charge and the depth of the discharge. Those things also. I don't the equation, state of the charge and the state of the discharge, that you will say that. It is a constant initially, that part. One more assumption also, what we are going to say that all the storage elements which are in fully charged condition, I mean by using of either some external source, that we have charged the supercapacitor part and the discharging operation that we are observing. Okay, that the discharging, how it is going to happen. This is the profile, means like when you are going for your electric vehicles, that you will say that quickly supposed to charge. For charging, that the current rating is supposed to be of high. Okay, that the current rating is supposed to be high, that the supercapacitors are going to provide that portion. If you see simple diagram that I have taken, that the switch, when you know that it is the input power and the output power that or load power that we can consider that this supercapacitor as a load, because we are supposed to precharge it. Okay, that if input power is greater than the load power, then the energy flows into the capacitor. Okay, if it is more than the load one, then the energy flows to the supercapacitor and it gets charged. If it is getting charged and it increases the voltage to a rated one, okay, that it reaches to the rated one, that voltage is going to be regulated. Energy flows into the capacitor and voltage across the capacitor is going to increase. If it is of less than, that the input power is less than the load power, here load is the supercapacitor, then it is going to that the voltage across the supercapacitor is going to decrease. There is in between, it is well and good for ideal cases, simple logic, that is the input power and the output power, that if it is greater than that, the power flows from the source to the load or from load to the source, accordingly that the voltage is going to vary. So now there should be some dynamics also that can be taken into the consideration. We cannot completely discharge the supercapacitor, we cannot completely, we cannot completely, when it comes to the charging, discharging part, we cannot completely discharge the supercapacitor. There should be some provision that we have to maintain. Okay, and first time that the supercapacitor charging is going to be of 100% from starting from the 0 to the 100. But second time that the charging of the capacitor, it is going to be 50 to 100%. Okay, 50 to 100%. That will be. So here, if you see that the power expression, rate of change of energy, that will be, you know, that of CV square input power minus output power, that is the change of the power. Here supercapacitor voltage, V1 is the initial charging voltage, V2 is the final charging voltage, alpha is the final discharge rate. Okay, final discharge that can be multiplied, that can be that the energy available, we mean to say that. So this is the simple, we have the different type of technique, constant voltage, constant current, constant power charging methods are there for the supercapacitor. Then we have, now when it comes, yeah, V, this one, yeah, okay, yeah, it is supposed to be V2 square, V2 square, yeah, V2, no, it V1 only, but what we are considering that it is the change of the final discharge. Okay, V1 minus alpha, for the first case it is of 100%, in the second case from 50 to 100% it is going to get charged, that it is multiplied with the alpha value. Okay, that is the thing. Okay, and then when it comes to this one, bidirectional DC-DC converter, okay, that what we are saying that during the charging condition, it can be of boost converter, in the case of charging condition, it is of buck operation, and in the case of a discharging condition, it is of a boost mode operation. You know that you are much familiar about this one, that is the off-bridge inverter module, this one, off-bridge inverter module, and so then this one off-bridge inverter module, what we are going to do, that power can be one upper switch and the lower switch that can be made to operate, that the combination, I mean to say that S1 and D2 will come into the picture, and here in this case that the S1 D2 K, then S2 and D1 will be in active, this thing, and then this parallel diodes which are connected across the switches when the load is in the form of a inductive in nature or of a practical RL load that can be taken. That the experimentation also that we have, that the experimentation is done for the resistive load, variation of the resistance. DC microgrid, how we are going to emulate? You are having a DC microgrid. Okay. So usually that the resistive load that we have emulated and did the experimentation. The system means like to the extent possible we reduced the cost, and the experimentation also it is not that much means like we can say that the power level is worked for the 240 watts. Yeah. So here during the charging mode that the bidirectional DC-DC converter is operated as a buck converter, and the power flows from the DC bus to the supercapacitor. While charging that the S1 and D2 will come into the picture. Okay. That when the switch is in on condition or off when the switch is in off condition. So here in this first diagram how the power flow it can be, that we mentioned the direction for the power flow for this one, which way that the power is going to flow for the first converter, this diagram. From? Supercapacitor. Yeah, that is the power flow is from the DC bus to the supercapacitor. Here the supercapacitor, what it is happening in the for supercapacitor, it is getting charged. Okay, it is getting charged in this case. Okay, when it comes to here that the boost mode, what's the operation? You know that the operation like a simple switch and the diode, that the switch and this LC filter is connected at the output side. Okay, here in the case of boost mode, how the operation power flow can be? Supercapacitor to DC bus. Okay, and you know always that for a boost converter inductive component is going to be in series, that the inductive component will store the energy here in this case, and then over the period that will be transferred to your DC bus. Okay, so during the discharge mode of operation that the bidirectional DC-DC converter is operated as a boost converter, and the power flows from the supercapacitor to the DC bus. Okay, in this mode that the S2 and the D1 are at going to be work. Okay, it is simple logic that the things now individually these two modes of operation are required for any kind of a storage system. Any kind of storage system means like that your PV panel, supercapacitor and the battery pack. Okay, this two modes of operations are of mandatory. I mean to say that these are the two modes irrespective of whatever the circumstances at the load side or of source side, the variations due to fluctuations, load demand and the fluctuations at the source side due to stochastic nature of your renewable energy sources or of distributed energy sources, that these two modes of operations are of mandatory. Okay. Now, if you see that after having this one, how this can be connected to a single system. Yeah, this is okay. One is the battery pack and the other one is of a supercapacitor module. This what kind of operation can we get? What operation that we get with this kind of leg structure, SB1 and SB2, and then this one is of SC1 and SC2. What operation can we get? SB1, SB2 and SC1 and SC2. SB1 and SB2, SC1 and SC2. These are independent, parallelly connected, that the systems are of parallelly connected. One, I mean to say that it is of independent. If you see that battery is there, inductive component in series, supercapacitor and inductive component in series, and the output is of DC, so DC load.
And SC2 and SC1 those are using to charging and discharging.
Yes, that is correct. Okay, that what we are trying to do that this will
make it common ground.
Yes, common ground, and then these two switches are going to provide the bidirectional power flow. Okay, initially SB1 and then opposite switch this one. Okay, and the other operation SB1 and this switch are going to come into the picture. This is what we mentioned here, that the individual operation. Two switches are exclusively meant for one storage system, that SB1 and SB2 are meant for the battery storage system, and SC1 and S2 are meant for the supercapacitor part. Okay, these are going to take care of the dynamics and the fluctuations and the required things to your DC microgrid. This DC microgrid, that the power can be made to flow from supercapacitor to DC microgrid or DC microgrid to the supercapacitor part. That way it is going to, that will be taken. And then even for the battery also, SB1 and SB2, the power can be made to flow from the DC microgrid to battery and the battery to the DC microgrid. This is the individual converter modules for the individual storage element. Both are connected in parallel. Okay, this two multi-source, that we are talking about the multi-source converter. Multi-source or of multi-input converter that we are talking. And here, if you see that when grid voltage falls below the set reference value, this one is of discharge operation. For discharge operation, you see that this one, which are the switches are going to be discharging operation, means that will be what kind of operation? Discharging means boost mode of operation. For this boost mode, SB1 and then this diode are inactive. Okay, will come into the picture to discharge the battery part. And then here also this SC1 and then this diode will come into the picture, then this converter is going to activate. And during the, what we can say that when grid voltage exceeds the set reference value, it is going to charge. Grid voltage exceeds the set reference value, it is going to, hybrid energy storage system is going to get charged. Here in this case, that the two things what we are having, one is the battery, that it is going to charging means buck kind of operation will be there. This switch, okay, and then this diode will come into the picture. For supercapacitor, this switch and then this diode will come into the picture. This is the operation of your hybrid energy storage system configuration. Don't consider that these are of only one single source. It is of two different sources are connected to the two different converters, and the control of these two converters are going to be of independent. This is what we are going to say, that the control which is going to be independent for these two converters. This one will form one converter and the other one is of this one. Okay, SC1 and SC2. That's the operation which is going to take place. Charging both the storage systems, I mean to say that it is supposed to get the charging and the discharging operation supposed to happen. Okay. Now I will give more detailed way about this storage system, that we have one side we connected the battery pack and the other side we have connected to the supercapacitor part. Okay. This is the DC bus what we are saying, and some dynamics that we have incorporated. Okay. To model and design the bidirectional DC-DC converter system for active hybrid energy storage system, we have employed controller using battery, supercapacitors and low power filter, low pass filter characteristic, battery, different disturbances. This is what we have. We generally neglect the battery control loop, low pass filter for analyzing. This is the, okay. Now you can see that the important thing is that the same structure that can be connected in this fashion. Okay. That will come. We'll talk about the while we are discussing about the control aspect. Okay. Now the structure operation that we are observing, then we'll discuss about this control loop operation. Okay. How the control loop. Now we are into the external sources, that the battery and the supercapacitor. This is the load part that we connected, and one load resistive load that we have taken into the consideration. How this power splitting also, the operation, now you see that what is output current, which is the means the summation of the battery current as well as the supercapacitor current. That I mean to say that here this one is going to contribute in this way, and the supercapacitor module is going to contribute to the same load configuration. Okay. This output power means like output current, which is equal to the combination of the battery current as well as the supercapacitor current. Here okay, we have the three things. One, what we can say that this is the output current, required output current, that is the 1 ampere means like that we have emulated, and how the reaction for the battery system and the supercapacitor. You see that the if you can observe closely that the red portion, red color indicates that the supercapacitor current, and then this green color is associated with your battery current, and then blue color is associated with the output current. Now, from this waveform, what is your observation? Which one is having the power density and which one is having the energy density? From this waveform, which one is having the higher density and which one is having the lower density? Yeah, how you will say that here? From this waveform, from this total waveform. Yes. Okay. Yeah. Okay. Yeah. Fine. Yes. Yeah. Okay. Blue one is the energy output current, that is the output current, and the red one is the supercapacitor current. So now the question, okay, these are the three currents that we are having, well and good. Okay. Now with one thing also that I can means instead of going also that I can make use of a battery alone, okay, or supercapacitor, which time is going to exist for long time, means like either this transient period or of steady state period is going to be longer. Which one? Yeah, steady state period is going to be longer period. You are going to run the system for more time. This is what you can see that, okay, that the green one is associated with the battery current, that the battery is going to supply the power to the load network. This will be exist for it becoming stabilized at this what we can say that nearly 4 seconds of time period, that the battery is going to be stabilized. Okay. And the supercapacitor part here less than that period itself, means nearly to 3 seconds, 3.5 seconds, it is going to be completely means like I mean to say that it is a discharge. It won't to supply the power after this period. Okay. Then the battery should come into the picture and supply the power to the load. Okay. Supply the power to the load network. This is what that the battery is going to do. And the supercapacitor part, it means discharges, it is not means like that the energy loss, means it is not in a position to supply the power to the load network. That is what here we can see that. But in this period, after reaching that the power splitting strategy that we are talking now, you talk about this thing at the means like 0.5 amperes. Who are the elements supporting to your load network? At the 0.5 seconds, which are the elements are supporting to your system? Yeah, both, means like both are trying to supply. Okay, both are trying to supply to the system. That is the 50-50%. And over the period, and if you see that this is the 100% system, we require the 1 ampere source. 1 ampere, that is the 0.5 can be shared equally between the battery and the supercapacitor. When it reaches that the 60% is the battery and the 40% is the supercapacitor part. Like this one, when it to 4 seconds of your period completely 100% by the battery, 0% this one. In that way that the algorithm can be written. This is the power sharing algorithm that we can say that we have that thing. So now your operation is understood. During the charging condition, the power flow is from the source to the load side, and then discharging from the load to the source side, You see that here this is the source that we have considered. Not to get confused, if you see that my student has clearly drawn the picture that the power flow here in this case, what we are having, that the supercapacitors are supporting to your load network output power. Here the battery also supporting to your load. Okay. This will be what we can say that during the discharging operation, it is of a what operation it can be? Discharging? Boost operation. Yes, that is the always it is in series with the source side, it is a boost operation. During the charging condition, it is of a buck converter. Now this load element is going to act as a source part. Load element will act as a source part, and then that can be given to your battery and the supercapacitor. Here in this case, that the battery and the surplus source power is there. This source power is of a PV, and it is more means like good amount of power that can be generated, that can be given to your battery pack as well as for the supercapacitor part. Here the same converter, we have the off-bridge model here. Depending on the switch configuration, that can be made to operate either buck mode of operation or of a boost mode of operation, can be charge or of discharge. So the same converter can operate in both charge and the discharge modes. Okay, by combining, this is the same structure that you are observing now from previous slide to this one, that the configuration is of same, but we are giving the detailed things for this one. The battery supplies the average power, and the supercapacitor compensate the transient power. Average power means the average power or of steady state condition, and the battery will support this portion. Okay, and then this is the all the thing is associated with the control logic, means like depending on this one, how much share of the load that can happen among the two modules, that can be done by using the algorithm. Yes. Then then afterwards, okay, the boost mode of operation is selected for the design of the converter to consider the effect of, okay, this will be control aspect that we'll see later on, but the output current which will be equal to the battery current plus supercapacitor current. Then next, this control aspects, what is the objective of our things, means like to have the hybrid energy storage system. One, what we are having to improve the battery lifetime. This is what extensively that we are having the discussion on it. Why the battery battery lifespan is of lower, to improvise that thing that we are going for the hybrid energy storage system. And also that the grid stability, this DC link voltage regulation or of stabilizing the DC microgrid, we are going for this kind of hybrid energy storage system. And also that one is lifetime, and also stress across the battery system, that the battery means response is of very low. Now even then also that you are observing that when you want to reach to the 100 kilometers per hour with short span, our engines are not supportive to reach. That is the reason our speed restriction is there for the electric vehicle. In what we can say that local transportation, that maximum of 40 kilometers per hour that can be taken, and then without license, that the government is promoting to have the electric vehicle, even then without registration and the license, that you can drive the electric vehicle. But due to this criteria, it can't achieve the speed at a faster rate. And then To balance the overall flow in DC link per source, and the load variations are categorized into two components, average power compensation and the transient power component. Okay? Average power component and the transient power component to balance overall, means like the overall system supposed to be balanced. For that, we are going for this hybridization of the two sources. This is the expression I mean to say that your output power, which is equal to the combination of both average power as well as the average, or we can say that steady state, and another one is of a transient power. It is simply P output into V output into I output. That can be of, it can be provided by the battery power as well as the supercapacitor power. Then the current part also will be given by this expression, that the total current can be divided it into the two factors. One is supplied by this one, and the transient and the steady state condition. This actually will come to the total current. That the total current is a combination of transient current as well as average current. I mean to say that. Yeah. If the if the transients are not handled in a proper way, what is the effect on your system? If the transients are not handled,
There is a possibility of failure of inductor.
yeah.
High spike in the voltage.
Okay.
It's going to disturb the inductor.
One is the failure and of the inductor, then the harmonics. Yes, harmonics are going to be, losses are going to be increased. Yeah, then. Yeah, fine. Yeah, I do give one example for you. You know that you have a kind of a two train systems. One is the kind of a goods train, and another one is of a passenger train is there. Okay, you take any of the train, means like passenger train and the goods train is there. You go and means like moving at one rate 100 kilometers per hour. So in short span of time, you will stop and move. What you are going to feel? A kind of a jerk, okay, uncomfort zone that you are going to feel. And if the goods are of sensitive in nature and do get damage about the goods, and it may not give the machine performance, also cannot be elongated. Machine performance is going to be degraded because of the generation of the heat and the jerk movement. That can be improvised by using this kind of hybrid energy storage system. That is the concept of having the combination of these two storage systems to improvise. When you are going, that the machine performance can be improvised, and your comfortness can be provided to the passenger system. Okay, jerk movement, that you himself, when the station is approaching, then driver will apply, loco pilot will apply the brakes on it, and then you feel that if he applies smoothly, that will be well and good, and suddenly he has to bring the speed to suddenly instantaneously zero, means there is a possibility of unevenness. Unevenness, as well as the passengers will feel uncomfortness. Okay, that can be, means improvise. This supercapacitor concept that can be employed in your, not only this kind of DC microgrid, means that is for the regenerative braking applications as well, and also some critical loads, something like your computer power supplies as well. And then this can be incorporated in the electric vehicles as well. That's the way that this supercapacitor part that can be incorporated in many of the applications. Not only bigger way also, that can be high power applications, static wear compensations also, that can be made use. But this is the technology, many means like that the people are working on it, and that can be, that you can soon or later that you are going to observe these concepts in the electric vehicles. Fine. Up to now, any questions or any queries, anything that you want to, you have?
There are many capacitors in the circuit.
Mm-hmm. Which one? Previous one? This one? Huh. This one? This one and this one, and here this one, no? Yeah, same, okay. You have two capacitors. These are the filtering. No, actually these capacitors are of what nature? These are of electrolytic capacitor. This electrolytic capacitor, this is not high rated capacitance. This capacitance is in the form of millifarads or of microfarad. Filtering purpose that they are making use. This won't be not plays significant role in the load contribution.
It is only used for stabilized purpose.
Yes, stabilized purpose. It is not going to, no. It is a standard structure of your buck converter. Here that we can see that, this is the buck converter, this one, and augmentation that we are making use of the filters, that thing. I mean to say that actual structure is of this one. Even then this inductive load also won't be there, but these two complementary fashion they are going to turn on, and then these filters are nothing to do with the load part, okay, just for the filtering purpose and eliminating the harmonic that they are going to make use, but it is not going to contribute the power to the load. And this here also that thing, filtering, which one is the source? Source is it is similar to like your DC source. These are battery and supercapacitors are a kind of a DC source only, that will be is going to able to provide the power to your network, okay. This one. So just imagine that the buck converter operation, but in a trivial way that we represented. It is a buck and the boost operation. Yes? Fine? Any questions? Anything? Yeah. Now charge and the discharge is associated with the buck converter and the boost converter. This is what it is there. Now I can go for little.
Small question.
Hmm.
Suppose you would like to discharge a battery
Yes.
while it is in the renewable energy system,
Hmm.
but it is already connected to the grid.
Hmm.
Suppose like vehicle to grid concept.
Mm-hmm. Vehicle to grid concept.
For discharging purpose, only we are going to consider the current purpose.
Hmm.
Is there or
We are going to for discharge purpose.
only current purpose we are going to consider?
Yes, obviously.
Because suppose we are going to consider voltage,
Uh,
for grid connected DC bus is always going to maintain 400 volts.
yeah. Okay. Yeah.
For some difficulty there,
Yes.
the discharge is not possible.
Okay. Yeah, fine. Means like that is the means we are not aiming to a high level. That the means like the standard thing, that is the 48 volts and the 24 volt system that we are considering. 400 volts, that you can imagine that the battery bank pack is going to be very, very huge. And
We have a setup, sir.
Uh-huh.
Electrical setup is there.
Okay.
There we have a lead acid battery with 96 volts,
Mhm.
with 96 volts,
Okay.
as well as we have EV battery system,
Okay.
lithium-ion battery, that is also having with 96 volts.
96 volts only.
96 volts and 20 ampere and 25 ampere.
Okay.
So we are going to planning to integrate this system to the grid.
Okay. Yeah, fine. Now you are saying that it is of a 96 volts. How many modules are there? I think that nearly 48 modules are going to be there, and the standard voltage rating of the battery is going to be of 2 volts only. That the 2 volts 48 modules will be there. You want to go to 400 volts, you can imagine that 48 into 4, close to the 200 modules which are going to be placed. And then afterwards, that okay, if all are performing well and good, all the individual battery packs are performing at same level, no problem. But if it is one, it is means like more active, and the other is not respondent and no response at all, then in those cases that the entire battery pack is going to shrink the lifespan. That we have to, for that only that we discussed about the cell balancing technique. Okay, that we have individual battery pack will have the individual converter, monitor the voltage level, make it uniform, so that optimal performance can be obtained. Okay, that the one statement also what we are going to say, whatever the manufacturer mentions about the lifespan of the battery, that the user is not going to get the same lifespan, because of in ideal condition that the manufacturer will mention, but our practical conditions are of different, we will not get the same thing because of these reasons. Okay, you that 40, I think that you can make a count also. We visited to one battery station, but the standard size is of 2 volt with higher ampere hour will be there. Yeah, fine. And also what another challenge that we are saying, that it is a chemical degradation, decomposition of the material, rise in temperature. Okay, rise in temperature. These are of some consequences that we have. Yes. Okay. Now we will make a move to the next thing. This one, it is interesting, our platform that we developed by one of my students with all the possible components that we placed here. That whatever I think that start with the DC source, but he has not projected. This is the DC source, I can say that, and another one is of a battery, simple battery model that we are having, and the supercapacitor part, and then supercapacitor converter part, this one, and supercapacitor converter part is this one, and the sensor circuit, and then DC microgrid, that the emulation, what we are saying that it is of a kind of a rheostatic load that we have considered. Measuring unit, and for generating the pulses we have how many, that the maximum how many switches that our system is going to happen, the 6 switches, but that even that PV panel also that we are considering, that this is the PV panel, it is operating under the MPPT condition. So now 4 switches are required, and the D-space system, 4 pulses that can be generated by using this kind of D-space 1104, I think, yeah, it is there. Controller is to be implemented using D-space DS1104 controller board. These are for development of this one. You can see that how much that is the interfacing system is here. It is good, you might have switched on, but you know this is the interfacing system that we have, and then this is sensor board which are made up of LEM sensor, and also battery, lead acid batteries, supercapacitors 58 farads, that will be 16 volts system, and then this is the, we have sensor board and the power board, I mean to say that, yeah, this is the power board, and then this one is of what we can say that it is of a driver board for generating the pulses to your switches. This is the power board, we can say that, and the source power supply that we are having. This is what that the person means developed the system, and we got the good fruitful results from this setup, and those are means like are published in the prestigious journal. Develop that the 2 input bidirectional converter for the hybrid energy storage system. Okay, and then I can show you individually that the converters are separate and the controllers are also separate. We are having the 4 parameters, one voltage control and the current control, then this one, and the individual converter modules also that we mentioned. Okay, developed sensor boards for current and the voltage by using the LEM sensors, and then Maxwell's supercapacitor of this series that we employ, 16 volts 58 farads that we have employed. Okay, this is what the supercapacitor that we can say, and then D-space, instead of D-space that you are little familiar about the disk space? How many are you working? How many of you are working with the disk space? Yes, any exposure to the disk space? For hardware interfacing, what type of circuits are you using? If you say, I can give more information. You have any hardware interfacing? You have vivid controller. Okay.
As well as FPGA with
OACOPC is there. Okay. Then?
Space also is there, sir.
Huh.
But we are not familiar. Actually, we are on the, now we are doing only simulation.
Okay.
I'm going to use those controllers.
Okay. Yes, this space, OpenLRT, LabVIEW, these things that you are making use. Yes, familiar? Yeah, one more that you are forgetting to know that one more thing also, that this DSP programming also. Yes, DSP also that can be done the programming by using this kind of Texas Instruments process that you can generate the pulses that can be given to your system, but it is somewhat, I mean to say that little outdated this one, but the advanced controllers are also there. It is similar to like your microprocessor or a microcontroller. It is a single chip but a standalone system that can be generated, but here the difference, what I mean to say that my students also to go for the DSP system, it is much easier as compared with the DSP programming. DSP programming that you require the more configuration, better about the means like familiarization about the architecture and the pin configuration, PWM generation, input output devices, those things are very essential. But the programming logic also, it becomes little tedious. Whereas in the DSP system that you can interface with your MATLAB Simulink code, directly it generates the pulses that can be given to your system, power circuit. In that way that the DSP is of more, what I mean to say that the DSP is of more, DSP is of more little complicated as compared with the DSP system. In this DSP system, DSP system, that the advantage is that means like you can run your MATLAB programming that can be transferred to your what we can say that is the DSP. It will generate automatically that the GUI files that can be generated. It produces the pulses to your system. This is what we can see that. Yeah, fine. And then we have, one moment. Sorry. Results part. When it comes to the, what we can say that the results part of your system, we have created the disturbances at the source side and created the disturbances at the load side. Okay, variation at the source side and the variations at the load side. We have seen the performance of your system. It is a standard system, that is the 48 volts we have taken into the consideration, and then we deliberately means like the testing channels like step signal we have taken and created the disturbance at this 0.2 seconds. Okay, there is a dip that you are going to observe. If there is a dip, the dip has to be supposed to be increase in current demand from what we can say that 4 amperes to the 6 amperes of current demand. Then who is going to support for this increase in current demand? That can be increase in current demand, that we can say that it can be supplemented either by supercapacitor or it can be supported by a battery part. So that 4 parameters that we measured, one with the grid voltage which is of 48 volts and the load current variation 4 amperes to the 6 ampere, battery current and the supercapacitor current. See that the response of your supercapacitor part means like very instant, means like very instantaneous. Instantaneously that it is responding to the variation of the load part. Okay, that there is a demand of 6 ampere, that immediately it is responding and trying to reach. Over the period that it is falling down and the current through the battery is going to be increased and it takes care. In steady state condition it becomes 0, but the this battery is going to take care of the load part. This is what we can see that, and the variation that we have done at the load side. Load side means like that the variation in the that is the rheostatic resistance that we have done, and we got this results part. Okay. Similarly, like your variations at the source side. This variation at the source side is due to what factor? Can you guess what's the source side, what we are having? Source side variations means?
Solar irradiation.
Yes, that the solar fluctuation means like it is of stochastic in nature, and then it is may not be constant output. That yes, disturbances at the source side. Yeah, that is intermittent or of stochastic nature or of prevalent nature, that we will call it, and it is not constant in nature, that the source power is of PV source or of any kind of distributed energy source, that you can say that, and it get disturbed, and this is the see that how the system supposed to respond by having hybrid energy storage system concept, that the battery current and the supercapacitor current is instantaneously there is an increase in demand of 1 ampere. This 1 ampere increase in demand is compensated by your battery part and the supercapacitor part. This is the dip, means rise in spike that we can observe here. This portion that we can means each period. If you observe that the transient period do exist for the longer period, and then this period steady state period transient period exists for the shorter period, and the steady state period exists for the longer time period. That's the reason, means like batteries are made to provide the longer period, and then this one is meant for the shorter time period, that I mean to say. Yes. Anything, any questions on this one, that the results part? This is the based on the simulation results alone. Okay, with the simulation that we got the things. This is the first first work done by first of my student, and got the publication, this one. Any results, any comments on this one? Yeah, we'll make a move to the next thing. Yes. So here that the experimental results, but it is rated for the 48 volt system, 20 volts per division that we have taken, and then similar disturbances that we created at a certain instances, we have seen that how the system response is going to be. Okay, DC bus voltage, blue color, battery current, battery voltage, and the super. It is a for getting my students 4 channel DSO. It is a 4 channel. Okay, he struggled a lot, and means like finally 2 or 3 days that he procured and got the 4 channel DSO and observed all the parameters. DC bus voltage, that we want to have the constant DC bus voltage system. Okay, it can be I think 24 volts only, because we did not go for the much higher voltage. And then battery current, 1 ampere, and this battery current also think 7 ampere hours. Yes, Siddharth, what's the battery pack we are having? 6? 12 volts? 12 volts. Current rating? 7 Ah. Yeah. So here in the case of most of you, that when you select the battery, that you will not ask for the battery power, you will ask the voltage and the ampere hour. What does it mean? capacity that you will ask. Means like suppose we have a battery of we have a battery of 12 volts, 7 ampere hours. What does it mean? 84 watt hour. Yeah, constantly with 12 volts, it will supply the 7 amperes of current for 1 hour time period. Okay, that is constantly, means that the capacity is going to be a ideal cases, that is the 84 watts, but 7 amperes for 1 hour time period. Okay, completely, that is the idea of selecting the battery. So here battery current and the load current, supercapacitor current, that the disturbances has created, and we got the means like short span, that we mitigated the variation of this one. Okay, if it is supposed to respond, that the time period is going to be, this one may not be great time period, that the transient period is of very short span, that what we can say, that we can curtail it, not exist for longer period. It is of very short period that can be mitigated within the stipulated time. Otherwise, means like heat generated by the system is going to be of more, that has to be taken care. Yes. So then, yes, and also here also different set of readings that he has taken into the account all the time, that we are all the 4 graphs, that we can see that there will be a constant voltage that is trying to maintain, that is the 24 volts he is trying to maintain. Here also that the battery current, and then this one load current and the supercapacitor current. Yes, here also this will be taken into the consideration, that the variations at the battery, supercapacitor, battery, and the output current. Okay, output current, battery current, disturbances that he has created and shown the things. So as on that the discussion, there is the work that can be battery and the supercapacitor are coming into the picture, and they are supporting it to the your DC bus. But our interest also will be the different, that this one individually acting according to the requirement of your load system. But it can be what we can say, that the energy exchange among the devices also should be taken into the consideration. That is the next phase of work. Means in the sense that if battery is having more power, that can be transferred to the supercapacitor, and if it is deficient, battery is deficient, that the supercapacitor should support to the battery. This is one. And also another module, PV module is there. If the PV module, always it is a source, we will not give the power to the PV module, but the energy exchange, these two things also should happen. That is the concept. Not only transferring to the load alone, and internally that the source of exchange also should happen. That is the work, the future that we can see. And then, few of the applications where we can see that combine the hybrid characteristics of multiple energy storage systems. It is mainly used in those applications where single energy storage system cannot perform at all, or with some limitations. Electrified transportation, renewable energy sector are some applications in which battery supercapacitor can improvise its metal. High power requirement of battery powered electric vehicles during acceleration, deceleration cannot be met by a single battery source. That these are the criteria. You know that during the accelerating period, what is the high current demand is going to be there. During the deceleration, that the energy recovery will be there suddenly, that just to maintain the voltage and the lower current. The type of power supply during the starting condition is going to be high current, low voltage power supply. Okay, opposite during the deceleration period. That can be done or can be developed by using this type of structure. Intermittent nature of renewable energy sources and ensuing power quality issues mandates the need for the battery supercapacitor configuration, which should have the characteristics of fast response, long-term energy balancing, short-term power quality, and the frequency regulation that can be done. Yes, fine. So now, when it comes to the conclusion of this topic, that the high power requirement of battery powered electric vehicle during acceleration alone, that can be increase in utilization of the renewable energy sources have augmented the applications of energy storage devices. Okay, all the distributed energy sources, without the storage element, it is hard to imagine the existence of your distributed energy sources. So it is supposed to be have the storage system, then only it fulfills the requirement. Without storing, you know, daytime I am comfortable, night time I am not comfortable, means it is not the criteria. So all the time it should provide the thing. So storage is essential and storage plays a crucial role. And then this concept relates fact that only advantages of the component are exploited while hiding their drawbacks at the same time. So something that one drawback associated with the supercapacitor is that low voltage rating. It is not meant for the line voltage, okay, not meant for the 400 volt. It meant for the low voltage. That is the drawback if you want to have series connection. And also there should be like a voltage balancing is required in the case of supercapacitor if you are going to make use for the your line configuration. Okay, and batteries also having advantages and the disadvantages. You know that even then also you are making it more popular to work with the batteries. Okay, at the end, as the electrical engineer, what we are saying that we are the end users of the batteries, not into the manufacturing side. That the optimal usage of the battery improvise the lifespan of your battery, that we are going to make use of this hybrid energy storage system concept. Okay. In the field of renewable energy smoothing, grid integration, electrified transportation sector, this battery supercapacitor is the most practical usage. Okay, most practical usage. So this is the work, and also good amount of publication, means like my students, we got it, all are of prestigious journal, and good work that it came. Okay, and that the produce, and also good response that we received, and also future also that we are going to continue in this work. Yeah. Yeah, fine. So anything that you want to have the questions?
Energy storage element can also have any role on system inertia.
System, yeah, obviously.
So they reduces or they can increase. Do we have any potential to increase system inertia also?
Yeah, that you know that the system inertia is going to improvise, and also what we mean, it is a energy reserve. I mean to say that it is also an energy reserve, but it is not for the long term purpose. It is for the short term purpose. And suppose that some faults which are going to occur, that the faults may not exist for longer period. It is for short period. 15 seconds or of means like 30 seconds that do exist, it can be mitigated by using the supercapacitor. And also that the reactive power compensation also can be done. This is there to means like we are saying that one of the application also it can be used for the power quality applications as well. Okay, it provides the system's inertia, but not for the long time. It is for the short time. System stability effect means like we are trying to maintain the constant DC voltage. Okay, that we created the disturbances and how fast that it is responding. This is what we have observed on the system. And when it comes to the life cycle enhancement, it is a long time consideration, but the system response that we have seen, it is good enough. It is a prototype model, not the industry scaled model. That we have made use 12 volts battery, 58 volts supercapacitor, and then this 0 to 100 volts DC source of think 0 to 100 volts with a ranging from 0 to 15 amperes DC source that we have made use for the hardware development. Yes, that it is free to access these papers and any queries also that can be discussed about this one, and also the control aspect that they yeah, yes sir. Yeah. Which where yeah, this one or this one? Ah, yeah. Yes. Yeah. A supercapacitor is negative in this way. Then what you see that according to your current demand, okay, now it is a decrease in demand. Here, initially it is of 1 amp, means like a dip in the current it is taking. That the what we can say that it has to observe instantaneous that the excessive current is there on the load side, then it has to observe. That can be immediately it reacts, it accepts the energy. In this case, now it, what we can say that supercapacitor is going to charge, not to give the energy. I am not going to give the power supply to the system. I am going to observe. That's it. Yes, this is the reason that it is dipping here and stabilizing out. Yeah, previous here. Mm. Yeah. Yeah. Fluctuations here that we are saying grid voltage, PV current and variations in the source power. Yeah. This portion. Yes, it is a switching. That can be of 20 kilohertz of operation that he has taken. Hertz. 20 kilohertz means like operating frequency of the converter part. 20 kilohertz of operation that we have taken into the consideration. It is a hard switching. Now this can be also extended the work to the soft switching and the dual active bridge isolated means like no, we don't want to go too much complication, that the things are of okay, and in a bigger way it has to be proven can be transferred to the industry. Means like that in add-on day for electric vehicle they are making use of the batteries, and no supercapacitor concepts is there in the case of electric vehicle. So we want to make it use for the supercapacitor part for the electric vehicles. Yes. Yeah, these are the things. Yeah, fine. If not, okay. That's. Yeah, fine. If you don't have the question, then we can break. So then after the break, we'll announce the things. Okay, the continuity of the session. 10 minutes. Inka 10 minutes. Yeah, fine. Yeah. Okay, fine. So then that will be another 10. This one. Yes. This diagram. What's the difference that you are going to observe from the results part and then this diagram, circuit diagram? What's the difference? Means I less focus because I'm not that much familiar. Now this diagram, number of switches are increased. Is it so? Only the switches. What is this configuration actually? Yeah, inverter. Yes, It is a three-phase inverter. I mean to say that it is of a three-phase inverter. Okay. If three-phase inverter is there, then obviously that we are making three-phase AC machine that we are using. And then this whole load, what's the earlier load? Resistive load. And then we made the inductive load here, means RL load that we made. And this configuration is similar to like your AC microgrid system. We want to have the both voltage control as well as the frequency control. To simplify this thing, that we made use of this one, means like inverter and the motor load that can be extended that the topic to the AC microgrids as well. And then similarly, if you see that the same configuration, we have this thing that the battery current and the supercapacitor current. How it is going to be injected, DC link capacitor will be there, then the output of this one will be given to your three-phase induction machine. This one also means, I mean to say that this is hybrid. Three layers are there. One, what we can say that hybrid energy storage system, multi-input bidirectional DC-DC converter, and the load part. This load part is of a AC microgrid system that we are having. And then, this one, yes. Then, okay. Any means like queries on this portion? Extra two switches. This one. Two.
We have only 4 switches
For
supercapacitor as well as battery.
Yeah.
But in this model we have
The configuration, if you see that to have the closed loop operation like this one, then they are making use this one. But the combination, I mean to say that S1, S2 is mandated either S3, S4. Each operation that they are going to make use of the 4. Then I mean to say that it can be also made it as a bidirectional power. Here, how many stages of connection that we can say that? One is the DC to DC, and the second stage is of a DC to AC, and DC to DC, DC to AC, 2 stage of conversion.
Sir, maximum how much gain we can transfer voltage in bidirectional conventional bidirectional DC converter?
Conventional DC-DC converter, how much power can you
Maximum gain
gain?
or ratio, transfer ratio.
Transfer ratio. The portion, like if you consider that depending on availability of your power at the source and the requirement of your load.
Suppose I need to convert from 400 to 96 or 96 to 400. Is it possible to use that conventional bidirectional DC-DC, or we need to use an extra DC-DC converter?
Yeah, you mean that you are talking about the GIAN DC-DC converter. Okay, that GIAN DC-DC converter is a different concept. It may not be the part of this work. GIAN means, like I understood, you want to increase the voltage rating by using the 10 times or 5 times of your source voltage, that can be increased. That concept is different. Yes, these controllers are purely made for the storage system, not for the increase.
I'm discussing about this. Generally with the storage.
Okay.
And bidirectional DC-DC converter.
Okay.
Actually, I want to implement my system as simple as possible, because my main area of consideration is the energy balance between the systems.
Okay.
So here, when we are going to transfer energy between the DC bus link as well as the battery, here suppose I am going to consider a voltage rating like 400 to 96.
Okay.
The gain around 4.
4
So,
times.
is it good, or we have to use an extra converter?
Extra is mandated. Yes, we can't.
Only the ratio of 2 is the
One, 2 times at the maximum that we can do, but behind 2 times it is difficult to increase the voltage. extra additional converter is required and the associated components is required. Yes. Yes, fine. Okay, we'll break and we'll continue afterwards.
Capacitor and it is charge below that rated. And
It is around 11:40. I will give 20 minutes time to discuss, means like prepare for yourself to explain about your research activity, what you are doing at your place, so that it can be useful for the rest of the other colleagues as well. In future, we want to have some collaboration kind of activity which will help you out for having this kind of discussion with them. Okay, you prepare, means like need not to be more. It can be up to 2 to 5 minutes that you can express about what you are doing, what the challenges that you are facing, and the motivations and the objectives behind your work, and also if you have any kind of structure that you can make use of. Means if it is PPT is there, that it is up to you, or otherwise just like means like orally, or you can use the board to express the things, so that the collaboration may happen among ourselves. Yeah, 20 minutes take time. It is a kind of activity that we do keep. Yeah, fine. Yeah, individual contribution, individual area, domain, and the research. Means like the kind of activity what you are carrying out at your places. Yeah, fine. Is it okay that the 20 minutes is time? It's fine. Navina, okay? You okay? Or more time is required for you? Yeah, fine. Yes, sir. Okay.
optimization algorithm for for both the PV and fuel cell, and then I have come to the analytical method. That is where it is completely of mathematical derivation, including I mean based on the equations. I am going to get the based on the equations, mathematical equations. I am going to assess the performance of the PV module and fuel cell in terms of its efficiency, maybe in terms of its performance indices like RMSE, SSE, MAE, NMAE, like that. So the other thing is these are the two things I am working on. The third thing is considering this same PV module and fuel cell in a small microgrid and assessing the some techno-economic analysis or life assessment of the different renewable energy sources. So that includes my research work of 3 aspects. Yeah. Thank you. Yes, sir. Two publications I have made, sir. One is SA, one is ESA. Yeah. Oh, no, they have to. Thank you.
Good afternoon, one and all. My name is Siddharth. I'm working. I'm doing PhD under Debasko sir. Currently, I'm in the 5th semester. My research area. My main focus is on the control system. In the before lectures, I told that about the controlling aspect. That is the conventional method actually. That is deals with the PA controlling. So there are many challenges in the linear control. As you know, PA tuning, we need to convert into, we need to linearize the transfer functions so that you will get here PA tuning. There are very advanced methods in linear control. Example like modulated control and steady mode control. Coming to modulated control, there are also many challenges. You need to model the system accurately, as there are too many different variables in the converter configurations. In the morning sessions, as I told, there are two converters, two bidirectional converters. So we need to model bidirectional converter into a model so that we can predict the future values. In PA tuning, it is a linear control, so it is not perfectly track the reference current. Coming to monoperative current, as it is a nonlinear property, it is including the dynamics of the system, so it can track the reference current very accurately, so that the dynamic performance of the system is very much accurate compared to the linear control. So my area is on the control aspect of the hybrid energy storage systems. And as I told that battery and supercapacitors, battery is a high density device, and supercapacitor is high density device. There is a challenge that low pass filter. The low pass filter is to divert the currents to the battery and supercapacitor. At that, in the morning sessions, I told that there is a cutoff frequency for low pass filter, which is a conventional. So we don't know exactly where is the cutoff frequency. Because it is a challenge. While we are in operation, the battery and supercapacitor, that the voltage levels may change because of the SOC of the battery and supercapacitors. We know that if you go beyond the limitation, like SOC of the battery or supercapacitor less than 20%, the output voltage at the output voltage across the battery and supercapacitor may not accurate. That may fall below that rated value. So that may introduce some oscillation in the DC grid. So we need to take care of that cutoff frequency. So my work is on the, I am doing on variable band fast filter with respect to changing the battery and supercapacitor of the SOC of the battery and supercapacitor. So that is my work one. And coming to my work two, which is a modulatory control. I want to introduce a modulatory control to the in the case of the PA tuning. So I don't want to tune the PA accurately because there are many challenges in the PA tuning. So I want to implement MPC for hybrid storage system for the improvements of the dynamic improvement of the dynamic performance. And I have done other work also that the power management between the battery and supercapacitor. As we know that there are many topologies in battery cell converters. That aspect itself is a very different area to do research because they have in conventional we have isolated and non-isolated bidirectional converters. Coming to non-isolated bidirectional converters, we have that we cannot control accurately because it is may introduce some of the inductor currents, some of the leakage currents. So if you are going for other topologies like that eigen converters, he has told me in the morning. If you go for eigen converters, it will give boost operation, but depends on the load and the configuration. You can have multiple aspects to design a converter. You can use non-isolated bidirectional converter. In bidirectional converters, we have that multi-input bidirectional converter also. In multi-input bidirectional converter, where you can exchange the power between the battery and supercapacitor also. So that work was done by my seniors. In that area also, if you implement if you implement modulatory control for high for such type of topologies, it will be a big challenge. So that is itself a research topic also. Thank you. Any doubts? Thank you.
Good morning, one and all. My name is Tirupati. Currently, I am working as an assistant professor in Guru Nanak Institutions, Hyderabad. So 6 months back, I registered for part-time PhD at NIT Warangal under the supervision of Dr. M. Uday Bhaskar sir. I have completed my coursework in the month of December, and I started my literature on EV charging systems. Mainly, I concentrated on onboard charging of the EVs. So onboard chargers means charging circuits integrated in the vehicle itself. So main challenges in the onboard chargers is by using onboard chargers, very less charging time is there, and also efficiency and thermal management. So I am looking to integrate the wide band gap semiconductor devices to improve the thermal efficiency and the efficiency of the chargers. So still I am doing my literature on the onboard chargers. Thank you.
Good afternoon to one and all. So myself, Dr. Chandrasekhar, presently working as associate department of Tripoli from Sri Venkateswara University, Tirupati. And I have been awarded a PhD degree in 2019. So my work was focused on minimization of torque and flux ripple for induction motor drives, precisely for synchronous speed and subsynchronous speed. So that was way back in 2019. And apart from that, so I was a great aspirant for postdoc positions. I am looking for some positions to work in research labs, maybe in IITs, NITs or in foreign. So I am exploring my chances and opportunities to get associated with research labs. And as part of that, and I'm attending some programs where I could get interacted with good faculty and good researchers, so that I can ask them and I can know what I can or what I'm deficient of that. And presently I'm guiding seven PhD students, and now they are working. So most of them, they are working on electric vehicles, and two students, they are working on the motor drives. So one is on BDC motors and the other person is on PMS motors. And two of the students, they are working on lithium and batteries. So they are focusing on the battery parameter, remaining useful life, state of charge, state of health, and apart from that, so I have put some research objective after completing my research. It is very fascinating for me also. So as soon as we complete research, even I have interacted with some research scholars here. So as soon as we complete our research, then we fix our mind like, so okay, completed, we have completed, and it is a lifetime goal and we have achieved it. But the problem, it doesn't stop over there. So the technology is changing day by day, and more advancements are coming in every field of engineering and sciences. So our objectives will definitely be modified. And my objective was, as I am looking for some research positions in lab, so I was to hope to change my domain or expertise. So with that intention, I have attended the program, and I was very attracted and motivated by the way how these distributed generations are playing a significant role in smart grid applications, and I have gained a lot of experience by going through the papers that honorable speaker was author of some articles. I have downloaded those articles, and I was all these days I was working on it, and I was seeing the expressions and modeling everything. And apart from that, so I have some as the Bhaskar sir was saying, so I was expecting some collaboration in the sense. So we are not so equipped with good facilities in the lab. So as we are from State University, we don't have such funding and good lab facilities. So I was asking the scholars from this institute, from this department, so how you are able to go with hardware implementation. So remember, like if we go with some experimental validation, then it will be very satisfying for our work. So I was asking the student, they were saying, so they have good facilities, so they have DSP programming and DSpace 1104 kit, so where they can work with some good and generate some good works. So in that sense, I can maybe formally or informally, I can request Uday sir to just make my students or myself to come over to this lab or to this department and work on those kits for in near future. So it is on cards. Maybe I'll be coming with some permission, or my students, I'm insisting them to come with rather than simulation, you come up with some real-time implementation. So in that sense, I can look into this formal permission to get access for the lab facilities that are available in this institute. And all the best for your future aspirations. Thank you.
Hello, thank you, sir. Very good afternoon, sir, and everyone here. I am Manoj Mishra. I am here along with my friend Rajesh Kumar Yadavendu. We are from IIT Mandi, APS, Advanced Power System Lab. The lab is actually supervised by the two professors over there. One is Dr. Pietros Mayes, he is our supervisor. Another professor is actually Dr. Tim Kundu. He works on, Dr. Tim Kundu works on power system and grid protection aspect size. sites. And our professor, Dr. Priyatosh Mahesh, works on system grid control and more kind of stability issues. Like. So I am actually I am looking to work on, this is my 4th semester by the way, and before joining IIT Mandi, I was assistant professor at Punjab Technical University in Chandigarh for the 4 years after my MTech. So my issues are actually what I have configured after literature survey. So there are few challenges with RES integration into the modern power grid. So first very important issue is the low inertia of the system, which when we actually integrate or try to integrate, and even when we integrate and then we operate the system, so we may have few challenges like security, safety, reliability, and some other issues. So the two important issues are voltage stability and frequency stability of the system. So there may be few main reasons of the system stability may be one is the system's decreased inertia, because RES integration sources, what we integrate like solar pig and like fuel cell or other sources, they offer very low inertia, system inertia. So overall this system's orbit inertia is actually becomes very less, and for any kind of disturbance it naturally goes down, damp out. So that is one of the main issue. Then lower voltage stability as a result of reduced energy distribution. This is one thing. And one more thing, because of decreased system inertia, there may be some angular stability issues in the system, grid type system. And the third one is lower frequency oscillations as a result of a shift in power sharing ratio when we integrate RES into our grid. Right? So the main challenges may be like if it is not engineered carefully, the integration of RES into the grid, then it may cause few like protection issues. So one thing, we are supposed to design a robust protection system for the grid having the option of RES integration. Then we can have control issues, power quality issues, reliability issues, and grid resynchronization issues. Resynchronization issues when the RES source or DC system is actually disconnected from the grid. Yes, and for this mainly I along with my professor is focusing on voltage and frequency stability issues more. There are a number of issues like protection and other. So Dr. Pratim's research scholar are working on focusing on protection issues. So I am planning to look into more on converter side for GFM technology and GFL technology for to cope up with the various security and these stability issues. Thank you. Thank you.
Before me, we both are working on the same topic under the supervision of the same guide and in the same college in the same lab. So it is very difficult for me to explain as he said. So we are concentrating on the problem facing in the research. Suppose we make a simulate mobile and output comes, but I don't know that output is correct or not. And if this is incorrect, which component we should improve? I don't know. If suggest anything that is good for
system. Okay, starting from your input till to the load point, how the signal is going to flow and what the changes will happen. That can be easily analyzed and interpreted and your command window. And then you can have the analysis where the system is functioning and how the things are going. If the system is of beginner, then the analysis is going to be more complicated. Make it part by part, that the system. Then have the cascading. My advice during the programming part of my students also what we are going to do, we'll ask all the parameters to write it on the command window. Then run that program. Then afterwards go to the Simulink, run your Simulink model. So that it will appear and something like unsatisfactory, satisfactory results are there. That the response that you will predefine for your either control or of your system, how the system is going to be supposed to be responded, then you can predefine. If it is not there, then you know if it is historical method approach is there, well and good. If not, also what we are going to do initially, most of the people will follow the trial and error method. Okay, change the parameter and see that okay, getting good with it. Then fine, okay. If not, then this is the utilized approach. Yeah, fine, and also expressing about your report. Yeah. Then next Navina.
Good afternoon, everyone. I am Navina from Andhra University. My research topic is stability improvement and overshoot damping in EV wireless power transmission. So I'm trying to maintain the stability in receiver set, that is buck converter, which is in the vehicle. So due to the changes in input like plug-in and plug-out of your power supply or any coupling changes, your entire system will undergo instability. So you will have large overshoot or large spikes in your battery current. So you need to maintain constant voltage and constant current in that system. So at present I am using PI controller and I am trying to maintain the constant voltage and constant current values, and I am trying to reduce the overshoot issues. So at present I am working on PA. Next I will replace it with another controller and try to improve, because with the PI controller, since as I increase the KP values, your system is trying to become stable, but your entire system response is becoming slow. So I need a better controller which gives a fast response, and at the same time it is minimizing the overshoot issues and maintaining the required constant voltage and constant current at the receivers at buck converter, that is the battery converter. So this is my research.
Yeah, fine. It's like you have the this one signal modeling.
Yes, I
Buck
have done the
converter.
mathematical.
Yeah, transfer function model, transfer buck converter. Yeah. And you are going for this kind of top switching technique or switching? Switching. It's like you are operating frequency of the circuit.
Sir, since it is wireless, it is usually high switching frequency. So I am using 85 kilohertz. It is usually starting from 25 kilohertz to about 50 kilohertz maybe. So I am using 85 kilohertz according to the standards of from standards that is from the IEEE.
Yeah, any publication from your work?
Oh.
You are in which year? Third year. No. Conference or something. Yeah, because it is a converter topic, so then better you should have for
My name is Vulala Pavani. I am selected as a JRF in ISRO sponsored project. In under the guidance of Nitwarangal, my guide sir name was Jayantil sir. My project title was development of motion controller for a full motion antenna. Full motion antenna will be fixed in ISRO organization only. I have to model a control system for the antenna, and for the two systems will be tracking system and motion position system. Tracking system, I have to control tracking system which monitor continuously the satellite, and position system which will when signal strength is higher, then it will stop the monitoring, and when signal goes to low level, then coming to some limit, we have to still on the position system, and it has this project contains a sensor system. Many sensors have to use, and signal detection and signal detection and control unit is digital signal processing. I have to model one digital signal processing, and in that analog signals will be converted into digital signals, and some processors also use it. I have to write a algorithm for the processor, and that algorithm given digital signal will be converted into analog signals, and it is given to the antenna. And for this to do two types ways are there: mechanical steering and electric steering. For mechanical steering, there is two complexity and cost will also more. Electrical steering only I am using. In that these are the elements we are using. Those are sensors, signal detection module, and control unit, digital to analog, DAC programming, and motor is easy to stepper motor and gear system and antenna. These are my topics. These are my topics.
Yeah, fine. Thanks for fine. Okay. Then afterward, okay. Now Gautam. Gautam is NIT and is working as a test guard. Okay.
Good afternoon, one and all. Thank you, sir, for organizing this GIAN course. As I am a PhD scholar from NIT Andhra Pradesh, my name is Gautam. I have completed my first semester, which is a course of 13 credits I have obtained, and I am currently doing literature survey on grid-forming converters. And this course is very useful. Right from the basics, the sir has taught us, and it is very helpful to me. And I want to go my literature survey on optimal placement of grid-forming converters, and as Manoj Mishra sir has said, stability issues, I want to carry out on that area. Thank you, sir.
Thank you. Thank you. Yes. Now, Arsha. Arsha is a JNU Hyderabad.
Well, good morning, good afternoon everyone. My name is Harsha. I'm pursuing MTech final year from Power System Specialization from Triple Department, JNU Hyderabad. So my final year project is about electrical braking. So I'm operating electrical braking in different modes of speeds, and I'm inspecting the battery temperature, battery power that coming from battery. So nowadays, mainly we have a flashing of electric vehicles in the Ola company. So due to increment in temperature. So I measure, I do my project in a similar way of the practical one. So in practical one we have different modes of operation like sports mode, economic driving mode. Similarly, those modes are analogous I do in MATLAB simulation. So I check in each and every mode the battery temperature. So if it exceeds some criteria, so then I stop the electrical vehicle saying that this increment the temperature can blast in the vehicle. So this project is under guidance of Dr. M. Shushama ma'am. So he's a doctor professor in GIAN Hyderabad. So that's it. Thank you.
Practical question. Overview about your work, and then this might be helpful for your work also. Most of the people are also working on especially that the staging of the overcharging, over-discharging, rising temperature, these are the critical aspects about your brand. Rahul sir, is there, professor at Vishwakarma Institute of Technology.
Thank you for this opportunity. Myself, Rahul. I'm from Maharashtra, Pune. I'm from BIT College. My department is different than electrical. It's not electrical. I'm from electronics, and my area of interest in robotics and robotics. Previously, I did power projects. Like I developed few products actually. I have my own company. Previously, now it is not there, but I developed few products, and even like our college has a tradition of doing real-time projects, live projects. So I'm working on EV now. So it's under non-disclosure agreement. So I'm not going to tell you the product, but we are working on an EV bike, which is Pune based, and we are developing all the sensor and interfacing for that. Even the power modes, different driving modes, etc. So we are working on that. They have already powered drives, right? So we are not going to design those, but we are going to monitor those things when the vehicle is running state. I believe real-time projects instead of research. Sorry for that. So I'll explain details, right? In details what I did. Like, I was a coordinator for LabVIEW Academy in our institute for almost 10 years. Even I'm a coordinator for robotics club in my college. That's why we are doing a lot of project in that. We delivered AGV, automated guided vehicle, for that's a robotic systems for different company like Ratna Gears, Atlas Copco and Ford Marshalls. Even we are working on drones. So one of my club is working on drone, and they are designing controllers for drone. Then previously I designed a product which is plating rectifier, which is generally used to plate nickel and silver or gold coating equipments. There we use rectifiers, general rectifiers. Their efficiency is very less, but what we did, we use high frequency rectifier, which saves the energy and obviously power. I have my own product, decarb machine, DC to DC. In that I use DC to DC converter for electrical, which decarb is a four-wheeler engine cleaner machine which we develop. Generally it is used to decarbonizing the engine parts, right? And there we utilizes DC to DC converter, which converts 12 volts to 5 volts and 12 volts for fuel pump. And again, in pandemic, we have developed ventilator-based systems. So that's it. We did these many projects. and we are really fascinated by these workshops, and obviously if we can help each other, we can do more projects and research. That's it. Thank you.
Yes, sir. Thank you. Thank you for giving the overview about your activities and teaching as well as for your research activities. Going into the electronics department, it plays a crucial role for electrical engineering as well in terms of the control point of view aspect, development of the signals using DSP process, harmonic these are crucial for us also. And now in our institute also, they do encourage to have the department collaboration. Yeah, that will be success most of the problem. So now with this we can close the session and we will have the session after the lunch hour. Yeah, after lunch will be served in the ground floor. You can take So tomorrow onward, that we will have the laboratory session, and the laboratory also will announce.
So we discussed about the three different types of the conversion system, grid forming, grid volume, and grid connected converter. So you know that grid forming is a form of current source, and grid following and voltage source, and grid connected can be also used for the regulation of voltage or grid. So then we discussed about the park and collect transformation, and we said that park is used because we can transfer from 3-dimension to 2-dimension, and after that we can actually the variable in fundamental frequency will be DC, so controlling will be much more easier for us. And for the Clark transformation also, we can change it from 3-dimension to 2-dimension, but then it's also sinusoidal with the 90-degree phase shift. So for the design of the control technique, we mentioned that we need to provide the dynamic model of the whole system, because we should see that impacts of each components in the system, in the changes in other parts. So the dynamic analysis started from the converter. So voltage is equal to phase voltage plus voltage of common mode. So by this we calculate the KVL from the system, and then we said that it is not needed. You go through the converter side, you can just simply say that we have a point, 2 point that between we can have some components, and based on that you can provide your dynamic model. So after that we replace with the voltage of the DC side to AC side, and we calculate the switching state function, and after switching state function we replace it to dynamic model of the system, and the matrix also can be reduced from 3-dimension to 2 because of we have no homopolar value and we have the balance system. So then we transfer the ABC to DQ transformation system, and the reason is that we are going to use for the control, because the filtering and the other part in DQ operation is much more easier. So for this we have phase 1, actually phase 2 and phase 3. So we transfer the dynamic model from ABC to DQ, and we reach to these equations. And we also notice that we have the coupling part in this equation, so it provide the negative impacts from d-axis to q-axis and from q-axis to d-axis. So then we use actually PLL, or we use by calculation of the V alpha and V beta, we could somehow calculate the instantaneous angle of the grid, and if we consider the direction of VD toward the reference value, then VQ will be equal to 0. So based on that, the equation can be also reduced one part, and then we provide the VD as a reference voltage for us. So now we consider also the dynamic model for the design of the controller, and we said that for this we use the PI controller, so we consider the LDI to DT plus RI equal to lambda, and lambda is also the change of the current times to P and Ki over the S. So we are just talking about what we discussed. Hey, welcome back. How are you? Long time no see. So you're better? Okay, I noticed yesterday in Hyderabad he was in the temple. Actually, this I don't know what they know. No, Chairman or no. That restaurant was he with the rice and chicken tandoori. Yeah. Yesterday. Okay, good. Now you recovered. Very good. So, two what? Surprise for me. Yeah, sure. Why not? You brought tandoori for me? So, okay, thank you very much. Yeah. Okay. So you bought something for me? Yes. Okay. Thank you very much. Ah, okay, tea. Coffee and milk. Okay, cookie. Thank you. Okay. Thank you very much. Yeah, thank you. Yeah, thank you very much. Thank you. Thank you. Thank you. Thank you and thank you. Okay. You yeah, sure, you can take 10 photos now. Yeah, thank you. Thank you. Thank you very much. I appreciate it. Yeah. I told you that I saw them in Hyderabad. Yeah, you remember? Ah, okay, living there. Okay. Okay, in the morning. Today. Wow. Okay, good. So, you're leaving us? Okay. Now the mission completed and return back to okay. Okay, good. Thank you very much, guys. So, now the question is from Arya that do you know why we consider delta I? Okay, no. So, you should listen, and then rest of the course will be also easy. I'm pretty sure that you can. Yeah, but listen carefully. I know that you were married, you were actually you had some problem, but now you're recovered. Okay, good. Good to see you again. So, I mean, we consider the lambda as LDI to dt to make our equation more easier, but then after delta I, we have actually this PI controller that tune the output current with the input current. So then we provide the actually model of the system based on the equation we get from here. But the only things that we consider was that, you know, after delta I, which is coming from the output current minus reference currents minus output current, we have delta I, and after that we have PI controller. So PI controller provide the way to follow the injected current, precisely the reference current. So we had also this coupling part, and the coupling part provide actually some impacts, negative impacts to the other one. So assuming that we are going to inject just 10 kilowatt power from converter to the grid, and you see that when we have this actually this power injection, we see the impacts of the coupling in the Q axis. But the expectation is that we just inject the active power. So for this, we use some virtual impedance, and based on that, we remove the impacts of the coupling and we decouple it. So we call it decoupling by this way. So by this, we have to separate actually transfer function, and based on this transfer function, we can easily provide the value for the K P and K I. But basically, K P and K I, because of the several other reasons, you cannot say that exactly can be calculated by this equation. So for this reason, we actually can get a quite good idea about the operation of the system, but you cannot provide the exact value. So for example, in K P, we have one omega n, and omega n is in somehow natural frequency, normally is very high. So for this case, if we compare the system, this equation K P with K I, we see that, for example, if this is 20, then it should be 400. So always you can say that, I consider something as a constant value, but far from each other. So if it is 50, you consider for K P, K I should be 2,500 something, but then play with the value, reach the right one. And how you can reach then to right value, you can actually check the value of the delta I, and you see that when it is getting better or not or worse, and then by this you can tune the K P and K I. So then we also consider the power equation for calculation of the active power reference and reactive power reference. And we say that, based on the objective of the integration, you can consider what kind of power you are going to inject. So in one case, if you are going to just inject the active power or combination of the active power in fundamental frequency or harmonic frequency, or later we saw that how we can actually calculate the reactive power injection. So based on that, you can decide that what is the share of the active power can be compensated, or reactive power can become, basically we are interested to compensate all reactive power, because then we should pay the penalty to distribution grid, but we have also, if we have extra power, we can also consider some part of the power injected for the fundamental frequency of the active power. So this is the model that you will use tomorrow for the simulation. It's not something, I think that at the first day, if you look at this one, it was very complicated, but nowadays I think that this is very easy for you. Am I right? Yes or no? At least you can say that there is nothing that I don't understand. For example, reference generation or generator, you must know that what is this, or probably PI controller, what is the idea we are using PI controller, or how we can calculate the switching state function from the equations, or about the alpha, beta, or DQ, and also how we can calculate the theta. But one aspect is this, and one is the tuning of the system. So basically, what I can say that, from my expectation, all of you guys should know that what is the reason that we are using this equation, but then you can apply by the simulation. So, any questions so far? No. So we discuss about the different types of the analysis, I mean simulation result, and yeah. This one? Yeah. Mm-hmm. Mm-hmm. No, you can actually, for the simulation, can consider the DC voltage source here. You don't need to consider this one because it doesn't matter if you have the AC source or DC source, but the idea is that we are using the DC AC converter. So we should have a DC voltage here, okay? And the idea of this chapter was to control of the DC AC converter. So by this assumption, the left side should be regulated DC voltage and right side should be AC voltage. Any other question? No. So now I just simply ask one question and then jump to the other. So, Dashida, am I right? Okay, good. Because I have a friend, his daughter is Arshida, then I think, okay, it was Arshida, then Darshida. Okay, so now I pronounce well. So Darshida told me that, explain that what is happening here. You were also Hyderabad, yeah? Okay, good. Seems that you are fresh and you had lots of fun. Okay, explain clearly that what is happening there. She's looking for an excuse, fall down, broken, and then said that, okay, now, okay, tell me. Clearly said that, I know that, pretty sure that you can answer. So, we start from here. From here. What is this?
We're tracking the reference.
You can use that one.
We're tracking the reference current.
Yes. What currents do we have?
Active current.
Yes, in the axis, yeah?
Yeah.
So you see that this is not DC, so it is a combination of, yes. So what is this?
A harmonic.
And fundamental frequency.
Yeah.
Excellent. So it means that the load we have is a nonlinear load, okay?
Yes.
So what is this current? What is this current? DG is connected to the grid, yeah?
Yes.
So compensate all the active and reactive power, okay?
Okay.
So, and this is also, you see that, it's all harmonic and fundamental frequency in reactive side is also compensated, okay?
Okay.
So, and when we reach in 0.2, what happens?
Increase the load.
Exactly. The load increase, okay?
Yes.
But we see that all reactive power are compensated, but some part of the active power are compensated, but you see it is not following exactly. And what is the reason?
Power is less than expected.
Yeah, exactly. The power actually we have available is less than the
expected.
The load.
Yeah.
Yeah. Okay. Excellent. Thank you very much.
Thank you.
Yeah. So by this assumption, we can conclude that you can control your converter in a way to inject any types of actually compensate any part of the load which is in the priority. So for example, if I have a load that needs reactive power, then my priority is not to compensate the active power. My priority is to compensate the reactive power, and if I find more power available, then I can go through the active power. Because buying the active power from the DSO is much more cheaper in comparison with the reactive power. So, now today we are going to talk about the operation and control of converter-based synchron generator. So it means that we have actually generator or DC-AC converter, but the reaction of converter is not like the previous chapter. It was not just a controller. It provides something else that instead of considering this as like a converter control, we are actually going to emulate the behavior of the synchron generator in operation of this type of system. So at the end of this chapter, you will be able to define the inertia and explain its rules in power system. You can emulate you will be able to emulate the behavior of the synchron generator using grid-connected DC-AC. What is this? Oh, okay. Okay, good. And you can provide the required inertia for power grid with grid-connected converters. Support the grid voltage and frequency regulation through grid-connected converters. So, before we start, what is inertia? You remember Costa? No, Abe? Yeah. So, if you remember it, I forget your name, sir. What was? Yes. Ramon? Rahul. So you fully remember actually Abe. And you know that he touched me and I touched him and he was a high inertia and I was low inertia, okay? So now briefly say that what is inertia? What is the definition of the, I mean, don't need go, just friendly say that inertia is like this, resistance, something like this, again changes or motion, something like this. So, can you provide the better definition of inertia in any system? So it's like our resistance against changes or motion. Yeah. Yeah. So yeah. You know, when you are in the bus, okay, so when we start to go forward, we see that, you know, we fall somehow left. And when we stop, we fall down, okay? So this is because of the inertia, which refer to the resistance to any changes. So any changes can be actually when we are in the motion time, it likes to go forward, and when if we are in stop, it doesn't like to go forward or changing, okay? So the inertia has this problem. Has this characteristic. So assuming that if we look at this one, what happens if hamster will suddenly stop, okay? So when it stops, you see that the inertia also, force him that, you know, just changing or rotating by this way. And if we see this one, the elephant stop, blowing air on pinwheel, we see that, you know, when stop it is still rotating, okay? So this is the inertia that, you know, when you stop imposing any energy or power, still it continue. So this is somehow the tendency to stay in the same situation. So in power grid also we have inertia to keep the reliability of the power system or stability of the power system. Basically, the reliability and stability of the power grid is coming from the inertia. So inertia is basically the main source that keep our system reliable. So assuming that this is the synchron generator, we see that we are in the grid and we have thousands of synchron generator provide the electricity and support the loads. So we see that this is actually different types of the synchron generator happening here. And we see one actually in this situation, the power we provide for the loads are the same, so we have a stable operation, so the number of the generation and consumption are in the same situation. But if a fault happening in this system, okay, so then still we see that all components or loads are working, and then some problem happening because the number of generation reduced, so it seems that generation are not enough to supply the loads. So it is like I'm walking and someone actually have a backpack, and then someone put a stone, 3 kilos of stone in my backpack. So it reduced my speed. So nowadays, we see that the generation, now there are some stress because the consumption are more. So for this case, we use actually, we measure the frequency, and for example, if the frequency is 60, we see that it dropped to 59 or something like this, and we have somehow a device, we call it governor, that detects the changes in the frequency, and based on that, it calculates and provide the information that what is the spin of the generator, and based on the situation of the frequency, it provides actually to change this spinning goes actually faster or slowing down. So this is somehow the main mission of the government. Then after some times you see that the frequency jump from 59 to 60 again. So this is like a cruise control in power grid. So governor detect the frequency, and based on that provide the information to the generator to increase the speed or reduce it. So when the fault happening, when the generation is less than consumption, it means that we need to increase the speed. So assuming that these things happening, so it means that the fault happened, generation actually detection has been done by governor because the frequency drop, and this is because of the number of the loads are constant but generation reduced, so generation are less than consumption. So then governor provide the information and detect it and provide the information to generator to increase the speed to somehow compensate these changes. So this is something that we need because we have the mechanical devices. We detect it and based on that react it. So it takes several seconds, and so what happened? So I have a problem, but I can survive. It means that some things keep my system still reliable and stable, even the problem happening in this network. And this is the duty of inertia. So this kinetic energy somehow provide the situation that all the loads running still in a stable operating condition during this transient time. So for, 5 seconds something, when the generation is not enough for the consumption, but still the network can stay stable. So this is the duty of the inertia. Any questions so far? Was clear? Yes? So, Siddhant, can you explain what is the responsibility responsibility of inertia in power grid? Look at my eyes and explain. Tell me. So, inertia is a energy. When the problem happened, it means that the grid should be unstable. So it means that, you know, the generation is less than consumption. But inertia keep the stability or guarantee the stability of the power grid during this transient time. So this is the meaning of inertia. So if you return back to the first day when I talked with the Abe, and then my body's inertia prevent to falling down, okay? So if I have less inertia or the grid has less inertia, it means the time for keeping this stability is less. And as much as we have more inertia, in fact the system is working more stable or longer time for the stability when the transient or some fault happening in the network. So is it clear so far, Udaya?
Yes. And what's the effect on the frequency about this inertia?
Yeah, I mean, yeah. Yeah. So basically when we have the less generation, so it means that the frequency be unstable. So in fact, this inertia support this fluctuation in the power grid, you know, in the frequency of the power grid. Yeah. Any questions so far? Is it clear 100% for all? Yeah? Arya? Okay. Yeah. Loader. Slow down what? Yeah. Yes. Mm-hmm. Yes. Generate. What happened? I mean, when the load is less than generation, so yeah. So, is it fine? So we can go next page. So nowadays we have a lots of target to provide the electricity from renewable energy sources, and then the main idea is that, you know, reduce the greenhouse gas emission, and for this case we need to use the power electronic converter as a heart of interfacing system between generation and consumption. So this type of technology are very very good when we have actually enough inertia in the power grid, but when the generation goes more than 30% in the power grid based on the renewable energy sources, then some instability issue in the frequency is happening, and this is due to lack of enough inertia for the power grid. So for this case, if you look at here, we have the renewable energy, we have the converter, we have the filter, and we have the grid. But the things that we are actually somehow lacking is that this type of technology cannot provide the rotating mass. They don't have rotating mass, and they cannot provide the inertia for the grid. And then the problem is happening for the stability of the grid. So what are the consequences of the technology? I mean, lack of inertia. Then we see that the frequency drop, and somehow stability of the frequency will be weaker, and when changes happening. So if you look at here, we see that we have a actually system with enough inertia and without enough inertia, and a fault happening in this time. So a fault or disturbance happening, overload or something happening, we see that, you know, the voltage drop, frequency drop is less. So you see that frequency from 50 goes to 49.96, but in this you see that it goes to, actually we have a bigger changes for the frequency. Why? Because the inertia is not enough for that one. And we have also some factor, we call it ROCOF, or rate of change of the frequency, and it's more dependent to the rate of the actually, it's like a, we consider the ROCOF based on the value of the frequency drop in the power grid. So if someone said that, okay, ROCOF of the system, it means that the RAM in the frequency actually we consider like a ROCOF. So up to here we see that, you know, we need in India, for example, we are going to reach the provide the electricity from renewable energy by 2070. In Europe is 2050. In Finland we are going to reach carbon neutrality by 2035. So, but the problem is happening because this type of technology are based on the power electronic converters, and this type of converters cannot provide the inertia. And so by this assumption, should we need to be worried about that one or not? Any idea? Yes or no? Darshida? Do you have any concern about this technology? Using or providing the electricity just by renewable energy in India? You say no. Yes or no? Why?
No concern because renewable energy is a need.
Okay, it's need, but it cannot provide the inertia and the system will be unstable. So.
But I think within the upcoming years, like the problems, whatever in the market we are facing, that may be sorted.
No, definitely it will be solved, but then how? You are an engineer, you are a smart guy, and then so you are going to build the future in India. So then do you have any idea about that one? Sami, do you have any idea about the problem appearing in the future of the network of the India if we have more than 50% renewable energy?
When we are going to increase the more renewable energy into the grid, whenever the fault occurs, it is going to perturb the other systems.
Okay.
The stability may lose.
But my question is something else. My question is that in India, we are going to reach the carbon neutrality by 2070, if I'm not wrong. I heard from someone. Then it means that we must increase the share of renewable energy sources, and this type of sources are connected to the power grid by use of the power electronic converter, which they don't provide any inertia for the grid. So it seems that future grid will be suffering from lack of inertia and lack of stability and reliability. So do you have any question, the solution for that? Or is it feasible to go from this direction or not?
Definitely requires solution. Definitely requires solution to provide inertia. That's why we are going to prefer those energy sources, energy storage devices.
By using the storage devices, provide the required inertia. How?
Whenever the fluctuation happens, if suppose our side like super capacitors is there, at the dynamic state initially those are more power dense devices. Whenever the fluctuation happens, immediately those are reacted and the sufficient energy is going to supplied by those super capacitors.
A super capacitor has a very limited capacity. Yeah, for sure.
And we are saying like that. The super capacitor is there, as well as the energy storage devices is there.
But the other energy storage are not that much fast enough. So there is something missing, okay? So we see it. Okay, excellent, thank you. Udaya, do you have any comment? It's fine up to now. Okay, so it seems that there is something missing, and then we must provide electricity from renewable energy. We need to use the power electronic, but if we go further than 30%, then we have the instability in power system. So now we see this one synchron generator. We see that using the conventional synchron generator is very, very important because they can guarantee, I mean, they have the rotating mass, they provide actually this, kinetic energy, and they are very strong against the changes, so they provide a very stable DC voltage in power system. And then by this assumption, we see that they are very, very good, but the problem is that we cannot use this one for the renewable energy sources. So this is some things that that we are suffering. But the question is that can we consider or emulate the behavior of the synchron generator in the power electronic based generator or not? So if we get back to the structure of this generator, we see that we have a DC current that applied to the rotor winding, and then we provide the magnetic field and provide then the other external somehow a provider like a wind turbine apply the power as a mechanical power and rotate the shaft, and based on that we provide the electricity. So by this we have actually somehow providing kinetic energy by this rotating mass, which support the stability of the grid. And basically this type of technology are coming from the swing equation of the synchron generator. So it means that P mechanici and P electrici. So it means that input power and output power, because we are talking about the generator, and the generator is a type of machine that convert the electric or some other types of the power to electrical power. So by this, our input is mechanical and the output is electrical, is equal to J omega d omega to dt plus d times to delta omega. So this swing equation is based on the frequency fluctuation under active and reactive power transition, which are limited by the inertia in synchron generator machine. So we have also damping factor, but this has a lots of mechanical and electrical limitations. So by this, they are actually damp the fluctuation, but they are not that much efficient to efficiently damp the fluctuation. So they are quite good and strong, but they are not feasible to be used for the renewable energy sources. But the solution for that one is that we use actually some type of technology based on the power converter, and also apply the behavior of the synchron generator in the control of the power converter. So for this, it could be converter-based synchron generator, or we call it VSG, virtual synchron generator. So it means that we use the converter, but control it based on the synchron generator model. And what is the benefit? The benefit is that we can integrate renewable energy sources to the power grid. Beside the active and reactive power injection, we can provide also inertia for the grid. So by this assumption, the grid, also the inertia in the grid increase by increasing these renewable energy sources to the grid. So if you get back in the 2000 something, 9 something like this, when they reach in the point that when we increase the share of renewable energy sources more than 30% in the power grid, then the inertia is constant and we reach to frequency problem. By using this technology, we see that we can provide required inertia for our system, and when we increase the share of renewable energy sources, in parallel, the kinetic energy also increase, and then grid will be strong enough to be survive. So if you look at this one, it works like this one, not like this one. So if you have a virtual inertia or providing inertia in the control loop of the converter-based generator. So now we have actually inertia constant, which we shown by H. So it represents the stored rotational kinetic energy in a synchronous generator or power system per unit power rating. It indicates or shows how much energy is available to resist frequency changes during a disturbance. So H is the kinetic energy stored in a rotor over the maximum power of the generator. So if we said that we have a 20 kilovolt ampere generator with the 1 kilogram over meter square J, it means that you should calculate the value based on the kinetic energy and divided by 20 kilovolt ampere, 20,000. So basically, mathematical model is expressed by this, because the kinetic energy is 1 over 2 j omega 2. This is from the elementary school or high school, middle school, that kinetic energy is 1 over 2 j omega 2. And S is the apparent power of the generator. So by this, H can be calculated by this equation. We call J, here also we had moment of inertia, and then we have omega G synchronous angular speed, and is rated apparent power of the machine, is the S. So, question, do you believe that if H is bigger, our system is stronger, or when H is smaller, our system is stronger? Smaller, bigger. Why? Okay, great. So when H is bigger, it means that the kinetic energy in power system or system is more. Okay? Then what is happening? So if we have less H, in fact we have less kinetic energy, and then if any changes happening in the frequency, we cannot damp it so fast. But when we have actually higher H, it means that we have more kinetic energy, and if any changes happening in the system, we can damp it faster. So just a simple example, but again return back. Does anybody can say that easily say that what is the H?
Unit of H is second.
Okay.
So it indicates in abnormal situation, machine transfer energy for that second, that much second.
Why? Why that much second? Not less or not more?
I don't know why less or more, sir, but
it's correct.
H is
why?
fixed.
So why that second? I mean, not more or less.
I don't know why more, sir.
Okay, but thank you very much. It's almost correct, but the first part. So does anybody has any idea what is the exact actually meaning of the H? Okay, let's see in the next example. So we have a 100 megavolt ampere machine which frequency is 50 hertz and has a moment of inertia 10,000 kilogram square meter. And now we are going to calculate the inertia constant in second. I give the material to you, okay? So we see that, okay, H is J omega 2 S. 1 over J omega 2 over 2S is J omega 2 S. And we see that we have the 100 meg and we have also 10,000. We have omega 2 and 2. Omega 2 is 314 y 2 pi f 2 times to 3.14 times to 50 is equal to 314. So the final conclusion is 4.93 second. But what is the meaning of this? I have inertia, I have a maximum power in a generator. Then we reach that H is equal to that value. What is the meaning of this? So if I have a generator that size or that size, what are the different things? What is happening? So any idea? So H equal to 4.93 means that generator can sustain its kinetic energy for about 4.93 seconds at full load before depleting. For example, if no mechanical power, for example, we have a turbine, we are actually providing like a shaft of the generator is supplied. The generator store energy would be used up in about 4.94 seconds at full load. So if it's a stop, it still can continue for 4.90 seconds. Okay? Did you get the point? Yeah, it's a time that it can continue the operation, because the reason for that that inertia is that if we get back the first page, we said that is a type of energy which wants to keep the situation as it is. So if you remember that elephant, you see that when they blew and they stop it, it's still turning on, and this is inertia, and it's happening also for the system. So when we get back to the power system and a fault happening, so if we had such a case like this type of generator, you have 5 seconds for the governor to detect the frequency, provide the right value, and then give to the other generator to go upper. So after this 5 seconds, close to 5 seconds, then some problem happening for the power grid. So it means that like you have actually 2 chain, and you have some vehicle. You can keep this one. Then after I don't know 5 seconds, you should leave it. Otherwise, your body will be divided in 2 parts. Actually, I'm not talking about our coordinator. He has more power. I'm talking about me. So, okay. Welcome back. You okay? You want to make a break or You want me to have a break if you feel tired? Okay. So you reach back 4 a.m., yeah? 2:30 a.m., okay. It was very bad time. 2 p.m. Ah, okay. Afternoon you are taking. Last night. Okay. Very complicated. You were also in Hyderabad, yeah? How was the nightlife?
Good, but like I didn't see much people in the night.
Much people during the night. Okay. But during the day, you went to Charman or
Yeah,
something? Okay.
too crowded.
Yeah, and the quality of the food was good?
Yes, great.
Okay, good. So you are not complaining means that everything was good. You are not complaining means everything was good. Yeah, good. Happy to hear. So, any questions so far? So seems that it is not that much. We are just getting a little bit step by step getting familiar with this type of things. But then later again get back a little bit to go further with some numerical exam. You see what is happening and you will be actually feeling it more. Just talking about some equation is not good enough, so we will get back again to this with some numerical exam later. Inertia what?
If the inertia of the generator is high,
Okay.
the minimum power required to run the generator, that is the problem.
I mean, when the inertia is high, it depended to the size of the system, and then, for example, if you have a generator in this size and that size, they are not the same. But it doesn't mean that we control something and said that we have something by this for this synchron generator. They are following with the equation. So if you have the j omega 2 times the 1 over 2, so then you can calculate it. But the system, when you go from the converter-based generator, so in theory you can say that I can provide 100% inertia, because we said that after 10% increment you should have 1.5% also inertia to share of the whole power and inject to the grid, so then you have enough inertia which not threatening the stability of the grid. Okay, but when we reach in the low inertia grid, so why we are not increasing from 1.5% to, for example, 5%? Do you know why? In theory is feasible, and we see that okay, we add this one and the storage we have, and then we increase something. But in practical, it makes the system, the generator, unstable.
One more thing, the wind turbine is there.
Yeah.
There is also the generator base, synchronous generator base.
Yes, but it doesn't provide too much inertia. Yeah.
Because of
Yeah.
wind speed, we are able to rotate the turbine.
Yeah.
If the inertia is high, it requires more wind speed to rotate.
No, then it makes some turbulence happening in the system. Yeah. Okay. Any questions so far? No. It can be one question for the final. This exam. So don't forget this number, 493. Okay. Yeah. So now we are getting back to the power system. In power system, we have a lots of synchron generator, and this type of technology are normally when we use in power plants, they are connected together in parallel. So by this, the output impedance of the system is less, and the system are more stronger. So when we are talking about the power grid, and sometimes we said that we have a strong grid, when sometimes we say that we have a weak grid. So what is the meaning of weak grid? What factor makes this grid weak? What? Impedance when it's very high. less in saturation. Oh, SCR is coming again to the impedance. Oh, yeah, but this is true. And any other things? So, yeah. So, I mean, when we have such synchron generators, in fact, we have a very strong actually output voltage. We have enough inertia, and then the other important thing is that this type of technology are connected in parallel. So if we get back to such a system, so assuming that we have one generator here, 2, 3, Tn. So if we connect them in parallel, and all of them has a Z, the same Z, what is the value of the equivalent? Z over 2 N is equal to Z equal. Yeah? So, assuming that I have these generations to connect the grid, I mean the load or anything, grid. So we see that we have a grid. The Z is equal to N, and this is the maximum power we can get from the power system. Okay? So Z over N. So assuming Z is 1000, and then we have 10 generators, so Z is equal to 100. Okay? So, and then Udaya is a representative of the Minister of Education, Energy and in India, and then they said that we are going to phasing out this generator, and one by one we exclude it because we provide some extra power from wind, solar. So as much as we build a new power plant or some sector for the renewable energy, we exclude one, like this. So if we exclude one, it's 1000 over to 9. Then again 1000 over 8. 1000 over 7. Okay? So you see that as much as we exclude the synchron generator and include the renewable energies, so it means that impedance is going up and upper. Yeah? The impedance increase. So when the impedance increase, in fact, the load changes provide the bigger impacts in the point of common coupling, and then the voltage or system will be more unstable. So get back to just a simple numerical example of this. So we have a grid is, 400 volt, and then we have Z equal to 10, and this is a load which the current is 5. Okay? So voltage drop here is 50. So the difference between this voltage and this voltage is 50 volt. Okay? And if we have Z equal to load, Z equal to 8, and then the same network, 400, 360, and delta V will be equal to 40. Okay? And then we go to the same grid 400, and then we have a load, current is 5, Z is 2. So you see that this is 400 and this is 396, and delta V is equal to, sorry, current is 5, Z is 2, so it is 90 and this is 10. Okay? Sorry, 2. So what is the meaning? As much as our grid impedance is higher, the difference between the voltage over the load or point of common coupling and difference with the grid voltage is more. We have more somehow drop. And any fluctuation here in the load current provide more impacts in the voltage over the point of common coupling. So the system will be always fluctuating because of the load changes. But when we have actually a smaller impedance, in fact the impedance over the grid is somehow almost similar to the voltage of the point of common coupling, and anything happening we have a stable voltage there. So by this, when we increase the share of renewable energy sources in power grid and also reduce the number of the synchronous generator, the impedance of the grid increase. By this, the grid become more, become weaker. Okay, so by this, anything happening, in fact, the grid is not as strong enough to damp changes, and we can say that we have very unreliable grids. Is it clear up to here? Yeah. So rest of your life, if someone asks you what is the difference between the weak grid and a strong grid, you can easily say that in weak grid, the impedance of the grid is high, so any changes in the load can have the big impacts over the voltage of the point of the common coupling. But in a strong grid, impedance is smaller or small, then by this the fluctuation in the current doesn't provide too much fluctuation in the voltage of the point of common coupling. So now we get back to the synchronous generator model, and we see that we have actually this this generator. So this generator, and this is our grid. So grid have the voltage, so based on that, the objective is to have a stable voltage here also, and then we have also synchronous generator that provide the electromotive force in the output of this generator. So we have also the impedance of the generator R plus L. So what we can see is that we have a voltage source here, which is going to connect the voltage of the grid, and by this we have a voltage with E, and the phase can be theta. Theta can be anything between 0 to 360, and the grid also have the theta of the grid, which also can be between 0 to 360. But because we don't have actually something like PLL, we cannot consider that what is the value of the theta in the grid. And always we have actually phase shift between the voltage of the synchronous generator machine and also the grid. So the difference between the grid impedance and the angle of the grid voltage and also the angle of the generator electromotive force is equal to delta, or we call it delta is equal to the theta of the rotating machine and grid. So if we consider this one, we can see that how much power can be injected from the generator to the load center. So if we have E voltage of the synchronous machine and also V voltage of the grid, so the active power can be controlled by the controlling of the delta, because the equation for transferring the or injecting power from the generator to the grid is equal to E times to V over to Z times to sine delta. So by changing the value of the delta, we can easily control the value of the active power which inject from the generation to the consumption. But regarding reactive power also we have the E, and then we have also this equation EV over Z cosine delta minus V2 over the Z, and the reactive power can be controlled by controlling the E, the voltage of the synchronous generator. So by this assumption, I mean, we can consider the E V over the Z equal to P max, and in some case that, you know, the difference between the angle of the grid and angle of the synchronous generator is small, we can consider the sinus delta is equal to delta, because it's very small value, and by this assumption P max sine delta can be shown by sine delta P max times to delta, not to sine delta, because they are almost the same. So is it clear up to here? You see that this is a source, this is another source here, and then because we have a generator, so it means that we are injecting power from the generation to the consumption, so the grid can be considered as a load, and we supply the load, and we can easily see the current injected from the E to V is equal to E minus V, but we consider the phasor, so E with the angle of the theta minus V angle of the theta times to over to Z is I, and then the voltage also can be based on the voltage of the grid. So easily we can calculate the power can be transferred from the generation to the consumption, or from the synchronous generator to the grid. Is it clear? This is the simple electric circuit to, you know, from the bachelor level in electrical engineering, so easily can calculate the active and reactive power from the machine to grid. Is it clear? So for the next stage, now we have actually this system V is equal to E minus Ri minus L di to dt. Is a dynamic model of the system. Is it clear? You want me to calculate it? Minus E plus L di to dt plus Ri plus V is equal to 0, so V can be calculated by this. So we can, using the Laplace, Vs equal to Es minus Is times to R plus Ls. Up to here is clear? Okay. Then if you are going to model this system instead of this, because we are going to model in the control loop, then we see that we have the current injected from the machine to the grid. So the current is coming times to R plus Ls, current times R plus Ls, and we have actually E from the synchronous generator, and E minus R plus Ls times to I is equal to V. Okay? So by this, we see that, we can model actually the operation of the system by mathematical equation. But the problem is that when we pass actually the current from R plus Ls, then this current, they have a little bit actually disturbances. Then we get the derivative of the disturbance, so it increases the value of the pollution in the current. So the measured current is affected by a derivative terms for calculating the voltage reference of the power converter. Okay, so did you get the point? So when current pass through this type of actually derivative, it increases the disturbances in the current. Because we are using the high frequency system, by default they have actually the frequency disturbances, then it increases the value. So then this is not a good idea to consider this one. Of course you can use it in the control of the converter, but what we are saying that we have the model of the generator based on the synchronous generator, and the idea is that we are going to transfer this behavior in the loop of the converter. And if we consider this one later as a converter, it means that the injected current from here, which is based on the switching, they have a high frequency disturbances, and when it passes through the Ls, in fact, it gets the derivative of the current, and it increases the disturbances from the converter to the grid. So for this case, Pedro Rodriguez is a friend of the Udaya. Yeah, he developed a technology, we call it SPC, synchronous power controller, and said that as a solution for this case, we get back to the same equation, but instead of considering the voltage model, we considering the current model. So again, the same equations, but it goes to E minus V divided by R plus Ls is equal to I. I is E minus V over to R plus Ls. Okay? So what is happening here? Again, we have a converter which injects the current, and we consider the voltage, measure the voltage, and we have actually this E and E minus V, E divided by R plus Ls. E minus V divided R plus Ls is equal to I. So now what is happening? Does anybody has any idea that why we are using this one? Instead of impedance, we are using the admittance. But what is the benefit, or what is the difference? Is there any benefit or not? Abe? You are the king of the inertia. Now, do you know what is the reason that we do these things? What? Short circuit. Why short circuit? Let's see. Yeah. Thank you. So you see that this R plus Ls working as a low pass filter. So instead of increasing the disturbances in the current of the converter to the grid, it reduces it works like a low pass filter and provide less distortion from the converter to the grid. So this is the benefit of this type of technology that we are going to use. So, any questions so far? So it seems that what proposed by Pedro Rodriguez was not actually complicated, but is very useful in comparison with the voltage model, which provide actually more disturbance from the converter to the grid. But still, we don't see what is the role of the converter here. Does anybody knows that what is the role of the converter here? No. Where do we see the converter here? Yes, but do we have converter here? Where is the converter? Yes, but we have also providing the reference, and reference is going to the control loop of the converter. So when we get back here, in previous session, we discussed about here. We said that, okay, it can be 10 ampere, and then we control the converter and measure the injected current from the converter to the grid, and by this I reference 10 ampere, then measure the current injected from converter to the grid, delta I, we have it, and then we have a current controller, PI controller, and by this we can tune the operation of the system. Copy and call can be tuned, and it works well. So what we do here is that we provide the virtual admittance. So the injected current we consider as a reference from the converter to the grid is somehow less polluted to the high frequency pollution, and by this we can actually ask about the current controller to provide them the power with higher quality. So what we discussed last chapter was this part. Okay? So it means that we provide the electricity and inject the power. So we can say that I reference is 10. We said 10 ampere, so we calculate the 10. If we get back to the previous chapter, so we see delta I. This is the injected current from the converter, and this is the reference. It can be load current, it can be harmonic, it can be anything you want, and the converter injecting based on that one. Okay? But what we are going to actually do here is that provide the reference for the control of the converter based on the behavior of the synchron generator. And then beside the provision of the active and reactive power, we can provide some supportive functionality to guarantee the stability of the power grid under dynamic operating condition. So up to here, we see that there is nothing complicated. Is it complicated so far? Now we are going to step by step to see that what is how we can actually modelize that one. We here. Hello? Yeah. We had too much, and we said that always we are going to provide the virtual inertia for the power grid and this type of thing, but I don't know, or probably we don't know how we can reach to this value. Still, we can say that, for example, Somi said that we can use the storage devices. Do I pronounce it? The battery is not working well. Hello? Okay. S-U-O-I. So, S-U-O-I. No, I'm saying that check from English to, or from Finnish to, if I'm not wrong. Suomi. Okay. Arya? Have you ever heard about this technology of the virtual synchron generator, inertia emulation? No. Yeah. Okay. What about you? No. So more than 1 week I'm talking about this and you never heard about this subject, yeah? Okay, good. Okay, good. So now let me ask one question. Okay. I cannot pronounce your name perfectly. So, introduce yourself again. Bruna Luni. Murula Lini. Murula Lini. Sorry. Murula Lini. You don't have nickname? Lini. Lini. Lini is much more easier also. Lini, we are going to provide the behavior of synchron generator in the control loop of the converter. Why?
So I don't know.
So relax. I don't know. Okay. So we talk about the PI controller, the control of the converter. Okay. Now we are talking about the using the model of the synchron generator, and then our converter react like a synchron generator instead of converter, just a converter which inject power. So do we have any idea, Lenny?
It provides the inertia.
Inertia, yeah. So, okay, excellent. Thank you, Lenny. You're smart. Okay, good. So, this is the only reason? Only reason. More maybe yes, maybe no. Okay, good. So, then if I get back to Arya and ask this question that, we are trying to go a little bit slowly, still we are in the beginning, but, it's like what is the intention for this? So why we are going to provide the behavior of the synchron generator in the control loop of the converter and say that the converter is working like a virtual synchron generator. So what is the reason?
We are giving it to the control loop, and the control loop from the control loop we are giving it to the converter.
Okay.
So like you are asking the reason. Yes. So like to get the feedback from from the control loop to converter, right?
Yes.
So, like we have to convert a particular parameter.
Okay. It is a so. What was your name? Anushti. Anushri. You explained clearly, then listen to her. Did you get the question? Why do we need, thank you. Why do we need to do this? Okay, let me say it differently. In previous chapter, we learned how to use the PI controller, and we saw that, by PI controller, you can actually measure the reference current and compare with the injected current, and after that PI controller. So we can tune the controller, and based on that we can inject active and reactive power and compensate the harmonic current components. Okay? So it means that whatever we want, now we can apply to the controller and obtain. So if I would like to get the reactive power from the renewable energies and compensate the reactive power, I can. If I'm going to compensate the harmonic, I can. If I'm going to consider the combination of the all things, I can. So everything is fine. Now the question is that what is the intention this chapter 5 we are going to do? Why do we need also go further? That one is not good enough? Anushri. Okay, Anushri, tell me. Your name is very, very hard for me. Okay.
No idea.
You don't know. Let me help you a little bit more. So we said that in 2009, the share of renewable energy goes more than 30%, and then lots of governments noticed that we have some problem for the grid frequency because it cannot provide enough inertia for our system. Is it correct? So do you believe the previous controller can provide the inertia for the grid? No. We can provide the electricity, but we cannot compensate. So what is the reason for this chapter? To learn how to provide inertia for the grid. Okay? Don't be afraid, okay? So it's pretty normal. I can say that, lots of people, or probably sometimes you don't know what I'm exactly asking, but we learn together, okay? So the idea is not that to make you a little bit guilty. The idea is that we understand we are in the same page or not, okay? So don't be sad. She was asleep when I explained. You at least were in the class. Yeah, okay. Lenny, am I right? You were asleep? Okay, yes, yeah. That's enough. Okay. So then, get back to you guys and you ladies. Do we really need to have this discussion in this chapter, and if yes, what is the reason that we need to provide the electromechanical model of the synchronous generator in the control loop of the converter? No? You are not interested? Okay, they are not interested to answer. Udayat, you want to say something? Yeah. So then the main idea is to consider actually, sorry. Yeah. Okay. So the main idea is that we provide supportive functionality beside the active and reactive power. So if we get back again, I say one time again that, for integration of renewable energy sources to the power grid, we need the power converter. This power converter cannot provide the kinetic energy for the power system. So then after increasing more than 30% energy from renewable energy sources, then we get in the problem of the instability due to lack of the inertia. So for this case, just providing this control loop and said that, okay, current is this one and inject power, that's off, is not enough, okay? So for this, in this chapter, we are going to provide some supportive functionality by controlling the converter and provide the, for example, inertia, voltage and frequency regulation for the grid, and increase the stability of the grid by integration of renewable energy sources to the grid, okay? So this is the main idea, that beside that current control, we add new functionality to operation of the converter-based generator. So we said that if we are going to consider this, we need to emulate the behavior of the synchronous generator, conventional synchronous generator, in the control loop of the converter-based generator. So for this, what we need is to see that what is happening in the conventional synchronous generator. So in conventional synchronous generator, we have actually the voltage and also the impedance of the synchronous generator. So based on the dynamic model, we see that, you know, we can modelize actually this part in the control loop of the converter. But when these things happening, we have the converter, and this converter is based on the switching, and the switching also provides lots of frequency, high frequency disturbances. So when we pass through this derivative part, in fact, we get the derivative of these disturbances and increase the value of the disturbances in the power grid. So in fact, we inject disturbances to the power grid. So by this case, we change the equation. We said that instead of following the voltage, we just transfer this one to here. E minus V is equal to R plus Ls to I. So by this, we have the I equal to E minus V over to R plus Ls. So what is happening here? It means that, you know, the current we are providing, this operate as a low pass filter. Instead of increasing the disturbance, it filters the disturbance, and we have a better shape of the current for the grid. So it works like a low pass filter instead of providing more actually a problem for the grid. One time forever, we are going to provide supportive functionality for stability of the power grid by emulating behavior of the synchronous generator in the control loop of the converter based generators. Okay, without that, we get in the problem. Is it clear for all? If I ask this question, it seems that everybody knows, yeah? Where is the Rakesh? Rakesh is not here? Yeah. I mean, it is not the constant number because it depends the grid, but they said that when we reach to 30%, it's something like this, okay? I mean, they said that based on the inertia we have in the grid, if you have 30%, then the changes happen. You said that the structure of the network should be considered. But basically, this conventional power grid are very strong. So if you say that 30% in American network, it is not like a 75% in Indian, or in Finland is not, I don't know, 55%. They are something almost similar. Yeah. Mm-hmm. Yes, but at the end, what we are looking for is not just this one. We want to see that our converter is operating like a synchronous generator. But they have some benefit comparison with the synchronous generator, because in synchronous generator we have a limitation due to just mechanical and electrical components they have. So this damping factor are not working very well there. So what we are going to see is that we have the benefit of the synchronous generator, and also we skip the drawback of the synchronous generator. So this type of technology can provide such a profit for power system. So if I go here, then I cannot stop here. I think that it's better that we close today, because I feel that some of students are a little bit tired. Yeah, you got the point? Everything is clear for you? You. Yeah, okay. Yeah, I noticed that. Thursday is much more better.
Thursday.
Yeah.
We will leave. We will close. The exam should be before that.
Before. You signed the. Yeah. Okay, let's ask them. So we should have an exam. What is the most convenient date for you? For the exam. You are going to take the certificate, okay? Then you should pass exam, okay? For example, Arya. Okay? I'm joking. Okay, don't worry. Yeah. But at the end, you should have an exam. I mean. Okay. So what is your preference for the exam dates? Wednesday or Thursday? Pattern? I can be like a multiple choice, something like this, and why? Okay. So what is the best day for you? More convenient? Thursday. Okay. Okay. So Tuesday we have just a simple exam. So be relaxed. Don't worry. So like a 10 multiple choice, question, and then so shouldn't be too and I don't know if we can go further or not. Yeah. Sorry? Tuesday, yeah. But it's not something complicated. Don't make your life hard for that one, okay? So it's a normal discussion, and yeah, it's a
Multiple choice.
yeah, multiple choice.
And
It's,
one more thing, that tomorrow's laboratory session is going to happen in the Smart Electric Grid Laboratory, which is there, located in the second floor of Electrical Engineering Department. Okay, we'll guide you to come over there.
yeah.
Directly.
Yeah.
Yes, morning, 9:30. After having the breakfast here, you will do breakfast.
No, it's okay? Okay. Yeah. I mean, when I talk, he says that, then he doesn't say that. Okay. Good. What is your name? Sean Ray? Okay. Shiravan. Shirvan. He's coming from the king, Anushiravan, like this. Shiravan. Oh, Sharavan. Sharavan. Okay, Sharavan. Okay, Sharavan. So I have nothing to say. If you want, I can continue by this, but I feel that lots of you are sleepy because of the, I don't know, course or some other things. So if you want, we can jump to the rest of this part in Tuesday. Yeah? Okay. So be present. It's an important topic. Tuesday morning, we have actually class. Afternoon, we have an exam. Yeah. Tomorrow, we have simulation class. Yeah. After what? We can continue?
No, it's the time of time is there.
I mean,
We started early, that is 2 o'clock. Supposed to start at 2:30, but we started at 2 p.m.
Okay, look, we have a syllabus for this course.
Yeah.
I will not leave the India before completing, okay? so don't be worried about that one, okay? So I promise. Yeah, we go for that, okay? Yeah. Okay. But you cannot learn model predictive all together in one course, okay? Because it's a topic of, I know this probably, you know, Jose Rodriguez from Chile, or Petros Carmanacos, or Vasquez, Sergio Vasquez. They are actually working whole life, academic life in predictive control. Or this Tobias Guerrier, he's a fellow of IEEE in MPC. Yeah. But we try to actually provide some information, then later up to you that how much you are going to go deeper. Yeah. So, Lenny, is clear for you? First part, no. Second part, okay, yeah? Okay, you were asleep actually. Not this first part. Okay, good. Excellent, so we see each other tomorrow. Yeah? Have fun.
Yeah, thank you. You can break for the tea. Tea is going to